Picture yourself floating in an almost perfect silence, the brilliant blue marble of Earth hanging peacefully below you. It's a view that has inspired generations, a symbol of human ingenuity and our relentless drive to reach beyond our world. But in that profound silence, there is another sound, one we rarely hear from the safety of our homes: the subtle creak of a spacecraft's hull as it battles extreme temperature swings, the frantic beep of a warning alarm, or the calm, yet strained, voice of an astronaut reporting a problem millions of miles from help. For every moment of breathtaking beauty in space, there exists an equally formidable danger, a hidden peril that remains just out of frame in our grand narratives of exploration. We often celebrate the triumphs of spaceflight, the flawless launches, the triumphant moon landings, the stunning images from distant worlds. But the journey itself is the most dangerous undertaking humanity has ever attempted. It is a realm where a tiny piece of debris, no larger than a paint chip, can strike with the force of a hand grenade, where the very vacuum of space and the radiation of the sun pose silent, invisible threats to both machine and mind. These are not just theoretical risks, they are the sobering realities that mission controllers plan for and that astronauts train to face, a constant reminder that the final frontier is as unforgiving as it is magnificent. In this video, we are pulling back the curtain on that reality. We are going to embark on a gripping journey to uncover 30 hidden dangers of space exploration, from the moment a rocket trembles on the launch pad to the existential threats waiting in the deep, dark void between stars. We will explore the psychological toll of isolation, the physical challenges that reshape the human body, and the technological vulnerabilities that could turn a mission to marvel into a fight for survival. This is a story of thrilling discovery intertwined with sobering truth, a comprehensive look at the perils that lurk just beyond our atmosphere. So, get ready to see space in a whole new light, because we are about to reveal what it truly takes to venture into the great unknown. And so we begin our countdown not on the launch pad, but with a simple, brutal mathematical truth that governs every single journey into space. It's a concept known as the tyranny of the rocket equation, and it is the first and perhaps most fundamental danger every mission must overcome. In its simplest terms, this equation describes a vicious cycle. To lift a rocket off the Earth, you need a tremendous amount of fuel, but that fuel itself has mass, which means you need even more fuel to lift that fuel. And then you need more fuel to lift that additional fuel. This creates a cascade where the vast majority of the rocket's initial weight, often 90% or more, is just propellant, leaving only a tiny fraction for the actual spacecraft, the crew, and the supplies. It's like planning a cross-country road trip where your car must carry all the gasoline for the entire journey from the very start, leaving almost no room for you, your passengers, or your luggage. This mathematical straitjacket forces engineers into agonizing compromises, shaving off every possible gram, often at the cost of safety margins and backup systems we would expect in any other form of travel. This relentless pursuit of lightness collides head-on with the violent environment of a launch. To break free of Earth's gravity, a rocket must generate unimaginable power, with engines burning thousands of gallons of propellant every second, creating temperatures hotter than the surface of the sun and pressures that would crush a submarine. These forces are contained by a delicate balance of engineering precision. Consider the intricate plumbing inside a rocket engine, a network of turbines and pumps spinning at tens of thousands of rotations per minute, forcing cryogenic liquids through pipes the width of a dinner plate. A single microscopic crack in a seal, a tiny flaw in a turbine blade, or a minuscule error in the software controlling the engine's thrust can upset this balance in an instant. The result isn't just a failure, it's a catastrophic disassembly, a term used by engineers to describe the violent, explosive end of a vehicle pushed beyond its limits. We have witnessed this tyranny in its most heartbreaking forms. The Space Shuttle Challenger, for instance, fell victim to a seemingly minor component, a rubber O-ring seal that became brittle in the cold and failed to contain the inferno within the solid rocket booster. That small, compromised piece, a direct consequence of the immense pressures and the unforgiving physics of launch, led to the loss of the vehicle and its crew. Every launch is a controlled explosion, a barely contained fury that we attempt to direct skyward. The rocket equation ensures we are always walking a razor's edge, where the margin for error is vanishingly small and the price of failure is astronomically high. It is the first great wall humanity must scale to reach the stars, a wall built not of stone but of fire, physics, and the cold, hard logic of mathematics. If the tyranny of the rocket equation represents a danger we must conquer to leave Earth, then the second threat is one that surrounds us the moment we arrive in orbit, an invisible shotgun blast of hypervelocity shrapnel that turns the space around our planet into a potentially lethal shooting gallery. We are talking about micrometeoroids and orbital debris, fragments ranging from tiny flecks of paint to spent rocket stages and defunct satellites, all whipping around the Earth at breathtaking speeds. In low Earth orbit, where the International Space Station and many satellites reside, the average speed of impact is approximately 17,500 miles per hour. To grasp the force involved, consider a simple paint flake smaller than your fingernail. At that velocity, it carries the kinetic energy of a bowling ball hurled at 60 miles per hour. Now imagine that energy concentrated on a point smaller than a pinprick. It doesn't just dent a hull, it vaporizes on impact, creating a tiny but powerful jet of superheated gas and molten metal that can puncture through layered walls, sever wiring, or rupture a critical fluid line. This leads us to a terrifying, self-perpetuating chain reaction known as the Kessler syndrome, named for the NASA scientist who first detailed the scenario. Imagine one major collision in orbit, for instance, a defunct satellite slamming into an old rocket body. That single event doesn't just create two pieces of debris, it shatters both objects into thousands of new fragments, each one a new high-speed projectile. Those thousands of pieces then significantly increase the probability of further collisions, which in turn generate even more debris. This cascading effect could, in theory, create an impassable field of shrapnel around our planet, a dense cloud of debris that would make certain orbital pathways too hazardous for satellites or crewed missions for generations. It's a catastrophic domino effect where our own discarded technology could potentially trap us on Earth, severing our access to the very orbits we rely on for global communications, weather forecasting, and national security. The reality of this threat is a constant daily concern for operations on the International Space Station. The station is equipped with hundreds of impact sensors, and its Whipple shields, a protective system named after its inventor, Fred Whipple. These shields are essentially layered walls. A small outer bumper is designed to vaporize an incoming debris particle, spreading the resulting cloud of plasma and fragments over a wider area so the inner hull can withstand the force. It's a brilliant design, but it has its limits against larger objects. The station regularly performs debris avoidance maneuvers, firing its thrusters to shift its orbit and dodge a tracked piece of junk. These are not rare events, they are a recurring part of station life, a testament to the ever-growing clutter in our celestial backyard. The challenge of tracking is immense. Space surveillance networks currently monitor over 30,000 objects larger than a softball, but they estimate there are millions of pieces between the size of a marble and a softball, and hundreds of millions of smaller, untrackable fragments that are still large enough to cause catastrophic damage. We have numerous tangible examples that bring this abstract danger into stark focus. Space shuttle missions often return to Earth with windows pitted and cratered from impacts with tiny paint flakes and metal bits, requiring the thick fused silica glass to be completely replaced. In 2009, a defunct Russian communications satellite collided with an operational American commercial satellite, instantly creating over 2,000 new pieces of large, trackable debris. More recently, the crew of the International Space Station had to take shelter in their docked spacecraft when a piece of debris from a Russian anti-satellite test passed uncomfortably close, a chilling reminder that a single irresponsible act can exacerbate the problem for everyone. This invisible environment of our own making is perhaps the most democratically dangerous aspect of spaceflight, a peril that does not discriminate between nations and threatens the future of space exploration for all of humanity. Having successfully navigated the violent physics of launch and the orbital gauntlet of high-speed debris, an astronaut might feel a moment of relief floating in the serene quiet of their spacecraft. But this quiet is an illusion. Here we encounter the third and perhaps most insidious danger of space exploration, an invisible, silent, and relentless bombardment that you cannot see, hear, or feel until it is far too late. We are talking about the omnipresent threat of solar and cosmic radiation, an environmental hazard completely unlike anything we experience under the protective blanket of Earth's atmosphere and magnetic field. Imagine being surrounded by a constant subatomic rain, a downpour of incredibly energetic particles that pass straight through your spacecraft's hull and directly through the cells of your body as if they weren't even there. This isn't a storm you can wait out, it is the permanent weather of deep space. This radioactive environment comes from two primary sources, each with its own terrifying characteristics. The first is a steady background drizzle of galactic cosmic rays. These are not rays in the traditional sense, but rather the nuclei of atoms like iron, silicon, and carbon that have been accelerated to nearly the speed of light by distant supernova and other cataclysmic events across the galaxy. Because they are so energetic and heavy, they are exceptionally difficult to stop. When one of these high atomic number particles slams into the wall of a spacecraft or an astronaut's body, it doesn't just stop, it shatters, creating a secondary shower of even more particles in a process likened to a microscopic shotgun blast erupting inside your tissues. Then there are solar particle events, the sudden and violent tantrums of our own sun. During a solar flare or a coronal mass ejection, the sun can hurl billions of tons of protons and other charged particles across the solar system at tremendous speeds. Unlike the steady cosmic background, these are intense, unpredictable storms that can deliver a lethal dose of radiation in a matter of hours to any astronaut caught without adequate warning or protection. The biological damage this radiation inflicts is both profound and multifaceted. As these high-energy particles tear through the body, they act like microscopic bullets, severing the delicate strands of DNA within our cells. Our bodies are remarkable at repairing this damage, but the constant cumulative assault can overwhelm these natural mechanisms. Unrepaired or misrepaired DNA leads to mutations, dramatically increasing the lifetime risk of developing various cancers, a primary concern for all space agencies. But the damage doesn't stop there. The lens of the eye is particularly vulnerable. Prolonged exposure leads to a much higher incidence of vision-impairing cataracts, a condition seen in many astronauts after long-duration missions. Perhaps most alarmingly, emerging research points to potential damage to the central nervous system. Studies suggest that exposure to heavy cosmic rays could lead to accelerated cognitive decline, affecting memory, decision-making, and reaction times. An astronaut on a multi-year journey to Mars could, in theory, find their ability to perform complex tasks and manage emergencies gradually eroding, a terrifying prospect when you are millions of miles from any possible help. The fundamental problem we face is that our current approach to shielding is woefully inadequate for the realities of long-duration travel beyond Earth's protective magnetosphere. The aluminum hulls of spacecraft like the International Space Station provide some protection, mostly from solar events, but they are almost useless against the most powerful galactic cosmic rays. In fact, when these heavy particles strike an aluminum hull, they can produce a more dangerous secondary radiation, making the problem worse in some cases. This has sparked an urgent search for next-generation solutions that sound like they're pulled from science fiction. One concept involves creating an artificial magnetosphere around a spacecraft, generating a powerful magnetic field to deflect charged particles just as Earth's field does. Another, more tangible idea is to use water or polyethylene, a plastic rich in hydrogen, as shielding. Hydrogen nuclei are so small and dense that they are exceptionally good at stopping cosmic rays without creating significant secondary particles. Imagine the walls of a spacecraft's sleeping quarters or storm shelter being lined with containers of the crew's own water supply, serving the dual purpose of hydration and radiation protection. For now, these are mostly concepts and areas of active research, underscoring the stark truth that before we can become a truly spacefaring civilization, we must first solve the puzzle of how to survive the very air or lack thereof that we intend to travel through. Yet another danger stands apart from all others for its sheer immediacy and visceral horror: the vacuum of space itself. If a spacecraft or a spacesuit were to fail, the human body would not explode in a dramatic fireball as science fiction often suggests. Instead, the reality is a silent, systematic, and brutally efficient deconstruction of life. The first and most critical threat is the explosive decompression of the lungs. The air pressure inside our bodies, which we are accustomed to at sea level, is suddenly met with a complete and utter absence of pressure outside. If an astronaut were to make the fatal, instinctive mistake of holding their breath, the air trapped in their lungs would have nowhere to go. The pressure differential would cause the lungs to overexpand violently, tearing the delicate alveolar tissues and rupturing them completely, forcing air directly into the bloodstream. This condition, known as an air embolism, would send bubbles coursing through the circulatory system, likely causing a fatal blockage in the brain or heart within moments. Simultaneously, a phenomenon called ebulism would begin. This term describes the rapid vaporization of bodily fluids. In a vacuum, the boiling point of liquids plummets. The saliva on your tongue, the moisture in your eyes, and the fluids in your soft tissues would all begin to literally boil away at normal body temperature. This does not mean the body would heat up, but rather that the external pressure holding those liquids in a stable state has been removed, allowing them to turn to gas. The result would be a dramatic swelling of the body, potentially to twice its normal volume, as subcutaneous tissues fill with water vapor. The skin, being surprisingly tough, would likely contain this swelling for a time, preventing a true explosion but causing immense distension and trauma. Your circulatory system would also begin to fail almost instantly. Without pressure to keep blood flowing properly, it would pool and stagnate, leading to a catastrophic drop in oxygen delivery to your brain. This leads directly to the third and perhaps swiftest killer: hypoxia, or a complete lack of oxygen. Even if you manage to exhale and avoid lung rupture, the vacuum offers no air to breathe. The oxygen in your bloodstream would be depleted in a matter of 10 to 15 seconds, and conscious awareness would fade almost immediately thereafter. There would be no time for a slow, peaceful drifting into darkness. It would be a sudden, involuntary shutdown as the brain is starved of its most critical resource. The historical accounts and testing from the early space age paint a chillingly clinical picture of this process. In the 1960s, NASA conducted experiments with animal subjects in vacuum chambers. The data showed that after about 90 seconds of exposure, circulatory failure was irreversible and death was certain. These tests were not done out of cruelty, but out of a desperate need to understand the absolute limits of human survivability and to design the safety protocols and suits that would protect astronauts from this most fundamental of space's dangers. All of this underscores one inescapable fact: a spacesuit is so much more than a piece of clothing. It is a personal, high-pressure, self-contained spacecraft, a miniature world tailored to a single individual. It must maintain a stable internal pressure, supply breathable air, regulate temperature from the searing heat of direct sunlight to the bitter cold of shadow, and protect against micrometeoroid impact. Every component, from the complex layers of fabric to the seals at the wrists and neck, is a barrier against an instant, agonizing death. This is why the preparation for an extravehicular activity or spacewalk is such a meticulous, hours-long process. Astronauts must pre-breathe pure oxygen for an extended period to purge nitrogen from their bloodstream, preventing the painful and debilitating condition known as the bends or decompression sickness, which can occur even when moving between different pressure environments inside the suit itself. The specter of a suit failure, a micrometeoroid puncture, a torn glove, or a malfunctioning seal is the primary, ever-present anxiety during any spacewalk. Every hiss from the life support system, every gauge reading, is monitored with intense focus because outside that thin, complex layers of material, there is nothing but a silent, airless void waiting. But after confronting the suffocating void, an astronaut must next face an environmental paradox that defies all earthly experience. A reality where there is no comfortable middle ground, only two simultaneous and brutal extremes. This is the fifth hidden danger, the relentless and unforgiving thermal swings of space. Here, the very absence of the thing that makes our planet so hospitable, a thick, protective atmosphere, creates a unique form of hell. On Earth, air molecules constantly bump into each other and into every object, transferring thermal energy in a process called convection. This helps to even out temperatures, carrying heat away from warm surfaces and warming up cold ones. But in the vacuum of space, there is no air, no medium to conduct or convect heat. The only way for an object to gain or lose thermal energy is through radiation, the direct emission of infrared waves. This fundamental shift in physics creates a terrifying split personality in the space environment, turning every spacecraft and spacewalker into a tightrope walker balanced between a blowtorch and a deep freeze. Imagine the surface of your spacecraft as it orbits the Earth. The side, bathing in unfiltered sunlight, is being bombarded by the full intensity of solar radiation. Without any atmosphere to scatter or absorb that energy, temperatures on sun-facing surfaces can skyrocket to over 120 degrees Celsius or 250 degrees Fahrenheit, hot enough to fry an egg in seconds and boil water away instantly. Yet, just a few meters away, on the side of the spacecraft cast in shadow, the story is completely reversed, with no warm air to provide even a hint of warmth, and with the craft itself radiating its heat away into the infinite cold of the universe. Temperatures can plummet to below negative 100 degrees Celsius or negative 150 degrees Fahrenheit. That is colder than the coldest temperature ever recorded on Earth. A single vehicle at a single moment in time is literally being pulled apart by these opposing thermal forces, creating immense mechanical stress as different parts of its structure expand and contract at wildly different rates. This presents an engineering challenge of nightmarish proportions. The delicate electronics, life support systems, and human crew inside the spacecraft can only survive within a very narrow band of temperatures, typically around 20 degrees Celsius. The craft's shell, therefore, must act as a highly sophisticated thermos, but one that is constantly being heated on one side and cooled on the other. Engineers achieve this thermal balance through a complex system of tools. They use multi-layered insulation blankets, sheets of thin, shiny material that look a lot like crinkly gift wrap, to reflect solar heat away and contain internal warmth. They employ carefully calibrated heaters to warm critical components in the cold and deploy movable louvers like Venetian blinds that open to radiate excess heat away into space and close to retain it. The heart of this system is the radiator, a crucial piece of hardware that looks like a set of flat, dark panels on the spacecraft's exterior. These radiators work by using a coolant fluid to absorb waste heat from the crew and electronics inside, then pumping that fluid through the panels where it can radiate the thermal energy out into the void. The entire design is a constant, active battle to maintain equilibrium, a dance between absorbing, reflecting, and emitting just the right amount of energy to keep the fragile bubble of life from either cooking or freezing solid. This brutal thermal dichotomy becomes intensely personal and dangerous the moment an astronaut ventures outside for a spacewalk. An extravehicular mobility unit or spacesuit is a miniature spacecraft, and it faces the same thermal extremes. The suit's white outer layer is designed to reflect sunlight while the inner layers provide insulation, but the astronaut's hands are perhaps the most vulnerable point. They must manipulate tools and grip handrails, which themselves are cycling between searing hot and bitterly cold. A handrail in direct sunlight can absorb enough energy to reach well over 100 degrees Celsius, while the same handrail just minutes later in shadow can plunge to cryogenic temperatures. The gloves are equipped with specialized silicone rubber fingertips that offer some thermal protection, but they are a compromise. They must be thin enough to allow for dexterity, which inherently limits their insulating properties. An astronaut must move with extreme caution, constantly aware that a seemingly innocuous piece of hardware could instantly inflict a severe burn or a frostbite injury. It is a constant, low-level threat that adds another layer of mental strain to an already perilous and complex task, a silent reminder that in the stark environment of space, even the simplest act of touching something requires careful thought and respect for the physics of a sun-scorched, shadow-frozen world. Now, let's shift our focus from the external environment of the craft to the internal environment of the human body itself, because after surviving the violent launch, the invisible shrapnel, and the brutal temperature swings, an astronaut is often confronted by a far more personal and disorienting adversary, their own physiology. Welcome to the sixth danger, the unsettling and often debilitating experience of space motion sickness, or what scientists clinically call space adaptation syndrome. Imagine the moment the engines cut off after launch and you experience true weightlessness for the first time. You are floating, completely unmoored from the familiar pull of gravity that has defined every single movement of your life since birth. At first, it might seem magical, but for over half of all astronauts, that initial wonder is quickly replaced by a profound and deeply unsettling sense of disorientation. It's a feeling akin to the worst seasickness you can imagine, but with no horizon to focus on and no solid ground to lie down upon. The root of this problem lies in a fundamental sensory conflict, a civil war between your primary balance systems. On Earth, your brain expertly integrates information from two main sources. Your eyes show you the world, telling you which way is up, and your vestibular system, the fluid-filled semicircular canals in your inner ear, senses gravity and motion, confirming the orientation your eyes are reporting. But in microgravity, this partnership shatters. Your eyes look around the cabin and see your fellow crew members floating in all orientations. There is no clear up or down. At the same instant, the tiny hair-like sensors in your inner ear, which normally rely on gravity to move the fluid around and signal direction, are sending chaotic, confusing messages. The fluid is floating, sloshing unpredictably, telling your brain that you are in a constant, tumbling freefall. Your eyes report floating while your inner ear screams that you are spinning. This conflicting data floods the brain, which interprets it as a sign of a severe neurological malfunction, most likely poisoning. The brain's primitive response to this perceived toxin is to make you nauseous, to trigger vomiting and headaches in a desperate attempt to purge whatever is causing the system failure. This is not a minor inconvenience. Space motion sickness can strike suddenly and intensely, severely impairing an astronaut's performance during the most critical phases of a mission. The first few days in orbit are often packed with complex, time-sensitive tasks such as checking spacecraft systems, preparing for a potential docking with another vehicle, or conducting initial science experiments. An astronaut struggling with relentless nausea, dizziness, and vomiting is in no condition to operate sophisticated machinery or respond effectively to an emergency. There are numerous and somewhat infamous anecdotes from the early space shuttle missions. Legendary astronaut Jake Garn, a United States senator who flew on the shuttle in 1985, was reportedly so severely affected that his name was unofficially adopted as a unit of measurement for sickness. A Garn represented the highest possible level of motion sickness. While humorous in retrospect, it highlights a very real operational risk. The crew has to adapt while simultaneously performing their duties, a tremendous mental and physical challenge that pushes human resilience to its limits. So, what can be done to combat this unavoidable physiological hurdle? Countermeasures have evolved, but they remain imperfect. Pharmacological intervention is the first line of defense. Astronauts are provided with a kit of medications, typically injections of anti-nausea drugs like promethazine, which are more effective in space than their oral counterparts because the digestive system itself is slowed down in microgravity. However, these medications often cause drowsiness, which is its own performance hazard. Beyond drugs, astronauts are trained in specific techniques to help their brains adapt more quickly. They are taught to minimize head movements, especially sudden turns or looking up and down, which can instantly trigger the conflicting signals. They learn to use their eyes to fixate on stable visual references, like the Earth's horizon out a window or a specific panel in the cabin, to provide their brain with a convincing up. Many find that staying tightly strapped in, providing some tactile pressure that mimics gravity, can offer a small degree of relief. Ultimately, for most people, the body does adapt. After 2 to 3 days, the brain essentially learns to ignore the chaotic messages from the inner ear and relies almost exclusively on visual cues. This process is called getting your space legs, but it's a miserable and unpredictable gauntlet that every new space traveler must be prepared to run. A stark reminder that our bodies are exquisitely, and sometimes inconveniently, designed for a world with a constant downward pull. Yet, even after the body adapts to the disorientation of weightlessness, a much deeper and more enduring challenge begins to take root in the mind. The seventh danger is not one of physics or physiology, but of pure psychology, the profound and unrelenting stress of isolation and confinement. Imagine being sealed inside a complex, machine-filled tube for months or even years, surrounded by the same handful of faces, with the endless black void of space pressing in on all sides. The vibrant sensory tapestry of Earth, the feeling of wind on your skin, the smell of rain on soil, the sound of a crowded street, is replaced by the constant mechanical hum of life support, the sterile scent of recycled air, and the sight of unchanging metal walls. This is not a temporary camping trip. It is an existence stripped of the very environmental richness that subconsciously grounds us and sustains our mental well-being. One of the most underestimated psychological stressors is the sheer mind-numbing monotony of the environment. While the work itself is complex, the backdrop never changes. Every day, an astronaut wakes up in the same small compartment, floats to the same hygiene station, and eats food reconstituted from the same limited menu. There are no weekends, no changes of scenery, no spontaneous trips to a cafe or a park. This sensory deprivation, the lack of novel stimuli, can lead to a state of apathy and lethargy that researchers call habitat fever. The brain, craving novelty and variety, begins to starve. Compounding this is the complete absence of any natural environment, a condition known as nature deficit disorder. Studies on Earth have repeatedly shown that access to greenery, natural light, and open spaces is crucial for reducing stress and improving cognitive function. In space, there is no green, only the manufactured interior of the craft and the breathtaking, yet utterly untouchable, view of Earth through the window, a beautiful reminder of everything you are separated from. This environmental deprivation is powerfully magnified by the social dynamics of living in a tiny, isolated group. You are trapped in an inescapable social contract with your crewmates. In such a high-stakes, confined setting, minor irritations that will be forgotten on Earth, the way someone chews their food, a particular habit of speech, a different approach to tidiness, can rapidly magnify into major sources of tension. There is no privacy, no place to go to cool off after a disagreement. This constant, forced proximity can fray the strongest of bonds, leading to interpersonal conflict, cliques, and communication breakdowns. On a long-duration mission, crew cohesion isn't just a matter of morale. It is a critical component of mission safety. A misunderstanding or simmering resentment between two crew members could compromise their ability to work together effectively during a life or death emergency, potentially dooming the entire mission. To truly understand these psychological perils, we look not just to space, but to the analog environments on Earth that mimic its conditions, such as the Concordia Research Station in Antarctica. During the 9-month winter, the station is completely isolated, with average temperatures plummeting to -80 degrees Fahrenheit and a crew of around a dozen people living in close quarters. Researchers there report a phenomenon dubbed the third quarter effect, where morale and mental well-being hit a steep decline around the 3-quarter mark of the isolation period. The initial novelty has worn off, the end is in sight but still feels distant, and exhaustion sets in. Crew members can experience depression, irritability, and cognitive slowing. These Earth-based studies provide a chilling preview of what a multi-year journey to Mars would entail, with one crucial, terrifying addition: the communication delay. On a mission to Mars, the comforting illusion of a connection to home would vanish. The delay for a radio signal to travel between Mars and Earth can be up to 20 minutes each way. A simple question and answer would take 40 minutes. There would be no real-time conversation with family, no live counsel from mission control during a crisis. An astronaut experiencing a deep personal loss, a moment of panic, or a severe conflict with a crewmate would be utterly, profoundly on their own. They would have to manage their emotional turmoil and resolve their disputes without any outside mediation, relying entirely on their own strained psychological resources and the bonds they have forged with their small crew. This level of autonomous psychological resilience has never been required of any human in history, and preparing for it represents one of the most formidable and least understood hurdles to becoming an interplanetary species. While the psychological pressures of confinement represent a battle for the mind, a parallel and equally alarming war is being waged within the astronaut's very body against the silent, insidious enemy of atrophy. This eighth danger, the systematic deterioration of bone and muscle in weightlessness, reveals a fundamental truth about human biology. Our bodies are incredibly adaptive, but they adapt for efficiency, not for health. On Earth, every single step you take, every time you lift a bag of groceries, even the simple act of standing against gravity's pull, provides a constant, low-level stress to your skeleton and musculature. This stress is not destructive, it is essential. It is the primary signal that tells your body, we need this bone density, we require this muscle strength. But in the microgravity of space, that signal vanishes. The body, in its ruthless logic, concludes that maintaining a robust skeleton and powerful leg muscles is a waste of precious energy. And so, the dismantling begins. The scale and speed of this loss are nothing short of shocking. Astronauts can lose, on average, 1 to 2% of their bone mineral density every single month they spend in space. To put that in perspective, a postmenopausal woman with osteoporosis on Earth might lose 1 to 1.5% of her bone mass in an entire year. An astronaut on a standard 6-month mission to the International Space Station could return having lost over 10% of the bone mass in critical weight-bearing areas like the hips and spine. This isn't just a number on a medical chart, it is a literal structural weakening of the skeleton. The bones become more porous, more brittle, and dramatically more susceptible to fractures. A simple misstep after returning to Earth's gravity could result in a debilitating hip fracture, a life-altering injury. Compounding this skeletal decay is a parallel erosion of muscle tissue, a condition known as spaceflight sarcopenia. The muscles that work the hardest against gravity on Earth, the calves, the quadriceps, the muscles along the spine, are the ones that waste away the fastest. Astronauts, despite being in peak physical condition at launch, can experience significant muscle mass and strength loss, leaving them weakened and physically compromised. The primary strategy to combat this physiological rebellion is as grueling as it is essential: a daily, mandatory 2-hour exercise regimen. The spacecraft becomes a high-tech gym, featuring specialized equipment designed to simulate gravitational resistance. The most critical piece is the Advanced Resistive Exercise Device, or ARD, which functions like a sophisticated weight machine, using vacuum cylinders and flywheels to create loads of up to 600 pounds, allowing astronauts to perform squats, deadlifts, and calf raises. They also use a specialized treadmill where the runner is held down by bungee cords to provide a load, and a stationary bicycle. This is not a leisurely workout. It is prescribed, monitored, and intensely demanding, a non-negotiable part of the job necessary to stave off the worst effects of atrophy. The mental fortitude required for this is immense. After a long day of complex scientific work, the prospect of a 2-hour, high-intensity workout in a windowless module is a profound test of discipline. Yet, for all this heroic effort, the current countermeasures are still only a partial solution. Exercise helps tremendously with muscle loss, preserving much of the strength and function, but it has proven far less effective at completely halting bone density loss. The mechanical load from the exercise equipment is different from the constant, omnipresent load of gravity, and the body's complex biochemical processes of bone remodeling are still thrown into disarray. Astronauts return to Earth with weakened skeletons, and while much of the bone density is recovered over time, studies suggest it may never fully return to pre-flight levels. Each mission potentially inflicts a permanent deficit. This reality casts a long shadow over future missions to Mars. A journey lasting up to 3 years could leave explorers so physically diminished that they would be unable to perform their duties upon arrival. Their bodies too frail to navigate the uneven Martian terrain in heavy spacesuits or to withstand the physical stresses of reacclimating to a gravitational field, even one only 38% as strong as Earth. They could arrive as pioneers only to be confined to their habitat, their bodies broken by the very journey that brought them there. But just as the body wages a war against the decay of bone and muscle, another, more mysterious battle is being fought behind the eyes of astronauts, a syndrome that took researchers by complete surprise and has since become one of the most worrying medical puzzles of human spaceflight. This is the 9th danger, the profound and often permanent impact of visual and intracranial pressure. For years, astronauts returning from long-duration missions would make casual comments during their post-flight physicals about their vision seeming a little blurry or that they needed new glasses prescriptions. Initially dismissed as minor quirks of adaptation, these anecdotes eventually coalesced into a disturbing pattern. A significant number of crew members were returning to Earth with measurable and sometimes irreversible changes to their eyesight. This wasn't a simple case of eye strain. It was a physical remodeling of the eyeball itself, caused by a fundamental shift in the fluid dynamics of the human body in microgravity. The root of this problem lies in a simple but profound redistribution of our internal fluids. Here on Earth, gravity is constantly pulling about 2/3 of our body's fluids downward into our legs and lower torso. Our cardiovascular system has evolved to fight this pull, with a powerful heart and a network of veins and valves working to push blood back up to the brain. But in the weightlessness of space, that constant downward tug vanishes. The result is what astronauts often call puffy head bird legs. Bodily fluids, no longer held down by gravity, migrate upwards toward the chest and head. Your face becomes rounder and fuller, you may experience sinus congestion, and your legs, freed from the fluid load, become noticeably thinner. While the puffy face is a temporary and mostly cosmetic effect, the consequences for the closed, pressure-sensitive system of the skull are anything but. This relentless fluid shift increases the pressure inside the cranium, a condition known as elevated intracranial pressure. Imagine your skull as a rigid, sealed container. On Earth, the pressure inside is balanced by the atmospheric pressure outside. In space, with more fluid pushing into that fixed space from below, the internal pressure rises. This increased pressure doesn't just push on the brain, it presses directly on the backs of the eyes, transmitted through the cerebrospinal fluid that bathes the optic nerve. Over weeks and months, this sustained pressure begins to physically distort the delicate structures of the eye. Medical imaging has revealed a suite of alarming changes: a flattening of the back of the eyeball, a swelling and creasing of the light-sensitive retina, and a protrusion of the optic nerve itself, a condition called optic disc edema. For the astronaut, the most direct symptom is a gradual blurring of their distant vision, a shift towards farsightedness that can make reading instrument panels or recognizing faces from across a room unexpectedly difficult. The long-term implications of this syndrome are a major wild card for agencies planning missions to the Moon and Mars. While some astronauts see their vision return to normal months after landing, for a significant portion, the changes are permanent. They return to Earth requiring glasses for the first time or with a permanently altered prescription. The true concern, however, isn't just the change in eyesight, it's what we don't know. Scientists are still grappling with fundamental questions. Is the primary culprit simply the fluid shift, or are other factors, like elevated levels of carbon dioxide in the spacecraft atmosphere, making the problem worse? What are the consequences of living for years with a chronically swollen optic nerve? Could this sustained pressure lead to a gradual, irreversible degradation of vision, or even an increased risk of glaucoma later in life? The frightening reality is that we are sending explorers on journeys of unprecedented length without fully understanding one of the most critical risks to their health and performance. Solving this puzzle is not just about ensuring astronauts can see clearly. It's about guaranteeing that after a multi-year voyage, they can still see at all. After confronting the disorienting effects of weightlessness and the slow erosion of bone and vision, an astronaut might seek solace in the one place that should feel like a safe haven, the controlled environment inside their own spacecraft. But here we uncover a 10th danger that is perhaps the most intimate and claustrophobic of all: the silent, creeping threat of a toxic atmosphere. Within the sealed metal walls, the very air you breathe can turn against you, not through a dramatic hull breach, but through a gradual chemical betrayal or a sudden, choking emergency. The spacecraft, a marvel of engineering designed to keep the vacuum of space at bay, can become a poison trap if its delicate internal balance is disturbed. The most immediate and terrifying atmospheric threat is fire. In the confined, oxygen-rich environment of a spacecraft, a single electrical short circuit or a malfunctioning device can ignite a blaze in seconds. Unlike on Earth, where smoke rises and can be vented in microgravity, fire behaves in a deceptive and deadly manner. It doesn't flame upward, it forms a stationary, glowing ball that consumes oxygen with terrifying speed and fills the entire module with thick, toxic smoke. There is nowhere for the smoke to go and no easy way to escape it. This nightmare scenario became a stark reality aboard the Russian space station Mir in 1997. A faulty oxygen-generating candle, a simple solid fuel device, burst into flames, creating a jet of fire that shot across the module. The crew fought the blaze with fire extinguishers, but for several agonizing minutes they were trapped with the fire, their vision obscured by choking smoke, facing the very real possibility of being overcome by fumes or having to abandon the station. That event was a brutal wake-up call, proving that even a small fire in space is a catastrophic event that can render the air unbreathable in moments. Beyond the risk of a sudden conflagration, there exists a more insidious, constant chemical background noise, the slow, steady off-gassing of the materials that make up the spacecraft's interior. Every piece of plastic, every panel of composite material, every adhesive, and even some fabrics release trace amounts of volatile organic compounds, or VOC, into the enclosed atmosphere. On Earth, these compounds would dissipate into the vastness of the open air, but in a sealed spacecraft they accumulate. Think of it like being sealed inside a new car on a hot day, with that distinctive new car smell. Except you can never roll down the windows and you are exposed to that concentrated chemical mix for months on end. These VOCs, which can include substances like formaldehyde and benzene, are known irritants and potential carcinogens. While environmental control systems work to filter them out, the process is not perfect, and crews are exposed to a low-level chemical cocktail for the entire duration of their mission. A chronic exposure whose long-term health effects are still not fully understood. Yet, the most fundamental and non-negotiable task of the life support system is the removal of the waste gas we all produce with every exhale, carbon dioxide. In the open air of Earth, CO2 is diluted to negligible levels. In a spacecraft, it is a deadly poison that must be actively and continuously scrubbed from the atmosphere. The systems that perform this task, like the carbon dioxide removal assembly on the International Space Station, are engineering marvels using specially treated zeolites to capture CO2 molecules from the air. But they are also complex mechanical systems, and like all machines, they can fail. A pump could seize, a valve could stick, or a sorbent bed could become saturated. If CO2 begins to build up, the crew would face a condition called hypercapnia. The progression of CO2 poisoning is deceptively gradual and deeply dangerous. It wouldn't feel like suffocation. It would start with a dull, persistent headache and a feeling of lethargy. As the concentration rises, it would lead to shortness of breath, confusion, and impaired judgment. An astronaut suffering from moderate hypercapnia might struggle to perform simple calculations or follow emergency procedures, their cognitive abilities clouded just when they need them most. If the levels continue to climb unchecked, it leads to convulsions, loss of consciousness, and ultimately, death. This isn't a hypothetical risk. On the early space shuttle missions, crews sometimes reported allowing CO2 levels to rise slightly to save power, only to find themselves feeling groggy and irritable, a clear sign of the system's critical importance. The life support system is the silent, unsung hero of every mission, a constant, humming guardian against an invisible killer. Its failure would mean that the very act of breathing, the most fundamental rhythm of life, would become the instrument of a slow, collective demise, a grim reminder that in space, even the air you rely on is a conditional gift maintained by a fragile web of technology. While we meticulously control the atmosphere inside our spacecraft, we have opened a new and profoundly unsettling biological frontier, one that carries risks not just for the astronauts but for the entire biosphere of Earth. This is the 11th danger, a dual-threat scenario of microscopic contamination that pits our quest for discovery against the fundamental principles of biological safety. On one side, there is the risk of forward contamination, the possibility that we, as interplanetary explorers, could become accidental colonists carrying resilient Earth microbes to pristine worlds and irrevocably spoiling our chance to find truly alien life. On the other side, lurking in the shadows of every sample return mission, is the far more ominous specter of back contamination, the nightmare scenario of an extraterrestrial microorganism for which no life on Earth has any defense hitching a ride home. The problem of forward contamination begins with the incredible hardiness of life on our own planet. We now know that certain extremophile microbes can survive the vacuum of space, intense radiation, and extreme temperatures. Species like Deinococcus radiodurans, nicknamed Conan the Bacterium, can endure radiation doses thousands of times greater than what would kill a human. These microscopic stowaways are present on every spacecraft we launch, no matter how clean we try to make it. They hide in the tiniest crevices, surviving the cleaning and sterilization processes. If they were to be deposited on a place like Mars, which may have pockets of liquid water or protected subsurface environments, they could potentially survive and multiply. The gravest consequence here isn't that they would harm any native Martians, but that they would completely overwhelm and obscure the very signal we are looking for. Imagine a future mission to Mars that, after years of development and billions of dollars, drills into the soil and excitedly discovers DNA. The celebration would be short-lived if we couldn't prove whether that DNA was truly Martian or was simply a contaminant we brought with us from Florida or Kazakhstan. We would have forever lost the opportunity to answer one of humanity's oldest questions: are we alone? To prevent this, space agencies adhere to strict planetary protection protocols, baking spacecraft components in giant ovens and assembling them in pristine cleanrooms that rival those used for computer chip manufacturing, all in an effort to be good guests in the cosmic neighborhood. But this concern pales in comparison to the chilling hypothetical of back contamination. This is the concept that has fueled science fiction classics like The Andromeda Strain, and for good reason. The core of the threat lies in evolutionary divergence. Every pathogen on Earth, every virus, bacterium, and fungus has evolved in a parallel arms race with its hosts for billions of years. Our immune systems recognize them, and our ecosystems have niches that they fill. An extraterrestrial microbe, however, would have evolved on a completely different world, along a biochemical pathway utterly alien to our own. It might not use DNA. Its metabolic processes could be based on entirely different principles. This means our bodies would have zero natural immunity, and our medical science would have no starting point for developing a treatment or a cure. It would be a biological blank slate, and its effects on Earth's life could be unpredictable and potentially catastrophic. The most frightening aspect is that we cannot even predict the mode of attack. It might not be a classic pathogen that seeks to use our bodies as a host. It could be a chemotroph that finds the iron in our blood a perfect food source, or a microorganism that releases a byproduct that is profoundly toxic to terrestrial life, effectively poisoning the environment just by existing. The scenario is not that it would necessarily be deliberately malevolent, but that its very existence is incompatible with our own biology. This is why any mission designed to bring samples back from another world, like the Mars Sample Return Campaign, is planned with a level of biocontainment that makes a maximum security virology lab look simple. The current plan involves a multi-stage fail-safe process. The sample container would be sealed on Mars, then launched into orbit around the planet. Another spacecraft would rendezvous with it, capture the orbiting sample, and seal it inside another, larger and incredibly robust container. Only then would it begin the journey back to Earth. Upon arrival, it would not land directly. Instead, the container would be designed to withstand a crash landing, to be retrieved and immediately transported to a specially built sample receiving facility, likely a biosafety level 4 lab with negative pressure, airlocks, and robotic handlers. The samples would be treated as the most dangerous substance on the planet until proven otherwise, studied in absolute isolation for years before any direct human contact is even considered. This isn't just scientific caution, it is a fundamental duty to protect every living thing on our planet from an existential threat we ourselves might bring home. After all the immense challenges of surviving in the hostile environment of space, the final, most fiery gauntlet awaits: the journey back home. This 12th danger, the perilous process of atmospheric re-entry, is a controlled catastrophe, a deliberate act of self-immolation where a spacecraft must use the very air of our planet as a brake, trading unimaginable speed for searing heat. Think about the physics involved. A vehicle like the Space Shuttle or a Soyuz capsule orbiting the Earth is traveling at approximately 17,500 miles per hour. That is over 20 times the speed of sound. To land safely, it must shed nearly all of that velocity. There are no brakes in space, and retro rockets alone don't have nearly enough fuel to do the job. So, the only way to slow down is to plunge into the thickening soup of Earth's atmosphere, allowing the relentless drag of air molecules to gradually rob the craft of its momentum. But that energy doesn't just disappear, it transforms. This transformation of kinetic energy into thermal energy is what creates the hellish inferno of re-entry. As the spacecraft slams into the atmosphere, the air in front of it cannot get out of the way fast enough. It becomes violently compressed, superheated into a seething plasma of charged particles that can reach temperatures of 3,000 degrees Fahrenheit or 1,650 degrees Celsius. That is hotter than the melting point of steel and even volcanic lava. The vehicle is, for several minutes, completely enveloped in a fireball, a shroud of incandescent gas that blocks all radio communication, creating the harrowing blackout period that mission controllers must wait through, hoping their astronauts emerge safely on the other side. Inside, astronauts report seeing a brilliant orange-pink glow illuminating the windows, a constant visual reminder of the furnace they are riding through. Navigating this narrow corridor of survival requires a precision that borders on the impossible. The angle of re-entry is everything, a calculated compromise between two equally fatal outcomes. If the angle is too shallow, the spacecraft will simply skip off the top of the atmosphere like a flat stone skimming across a pond, bouncing back into the endless void of space with insufficient power or life support to ever return. But if the angle is even slightly too steep, the deceleration forces become unbearable, subjecting the crew to crushing G-forces that would render them unconscious, while the intensity of the heat skyrockets, overwhelming the vehicle's protective systems and leading to certain disintegration. The target is a window barely 1 degree wide, a razor-thin slice of possibility that pilots must hit with flawless accuracy after a journey of millions of miles. The only thing standing between the crew and this plasma inferno is a seemingly mundane yet critically complex component, the heat shield. On the Space Shuttle, this was a system of over 20,000 individually crafted tiles, primarily made of a silica fiber that is 99% pure air. These tiles were so delicate that you could crush them in your hand, yet they possessed phenomenal insulating properties, able to withstand the searing heat on their outer surface while the inner surface, glued to the shuttle's aluminum skin, remained cool enough to touch. The integrity of every single tile was paramount. A single gap, a single compromised section, could provide a pathway for the superheated plasma to seep inside, burning through the vehicle's structural skeleton with the efficiency of a blowtorch. This is not a theoretical risk, it is the tragic lesson burned into history by the Space Shuttle Columbia disaster. During Columbia's launch in 2003, a piece of insulating foam broke off from the external fuel tank and struck the leading edge of the shuttle's left wing at a relative speed of over 500 miles per hour. To engineers on the ground, foam seemed insubstantial, but at that velocity it acted as a solid projectile. The impact, unseen and unknown to the crew, punctured a hole in one of the reinforced carbon-carbon panels that protected the wing's leading edge, the point that endures the very highest temperatures during re-entry. As Columbia began its descent 16 days later, it was unknowingly flying with a fatal wound. When it entered the atmosphere, the superheated plasma funneled into that breach. It first began severing internal sensors, sending erratic readings to the crew and mission control. Then, it systematically melted the aluminum support structure of the wing from the inside out. Within minutes, the aerodynamic stability of the vehicle was destroyed, leading to its breakup over the skies of Texas. The crew, aware that something was terribly wrong but powerless to act, perished. The Columbia tragedy stands as the most devastating testament to the unforgiving nature of re-entry, a stark reminder that the journey home is not a triumphant conclusion, but a final, high-stakes battle where a single, small flaw can lead to catastrophe, and the margin between a hero's welcome and a national tragedy is thinner than a piece of foam. Emerging from the scorching plasma of re-entry, a spacecraft has conquered the fiery gauntlet of atmospheric friction, but the mission is far from over. The 13th danger lies in the final, desperate grasp of gravity, a phase where success and disaster are separated by mere seconds and inches. After the monumental effort of leaving Earth and surviving the void, the simple act of landing back on a planetary surface presents a gauntlet of unpredictable and violent challenges. For crews returning to Earth, the journey often ends not on solid ground, but in the open ocean, a seemingly soft landing that conceals its own set of treacherous variables. The concept of a splashdown might appear straightforward. A capsule parachutes into the water and waits for recovery. In reality, it is a jarring, disorienting, and highly dangerous event. The ocean is a dynamic, living entity, not a placid landing zone. Imagine a capsule hitting the water at nearly 20 miles per hour. The impact is severe enough to injure astronauts who are already physically weakened from their time in space. But the true peril begins the moment the capsule becomes a boat, or more accurately, a vulnerable canister adrift in a vast and powerful sea. A rogue wave, a sudden swell several meters high, can roll the capsule over, leaving it floating upside down in what is known as a stable 2 position. The crew, now disoriented and hanging upside down in their harnesses, must then initiate a complex and physically demanding procedure to right the capsule, inflating airbags on one side to flip it back over, all while combating seasickness and disorientation. Even a perfectly upright capsule is not safe. The same hatch that kept the vacuum of space at bay can now become a deadly liability. If the seal is compromised by the impact, or if a wave crashes over the hatch at the moment it is opened for recovery, seawater can flood the compartment in seconds. The capsule, designed for the weightlessness of orbit, is not a seaworthy vessel and can quickly swamp and sink, trapping the crew inside. Alongside the risk of drowning is the ever-present threat of hypothermia. Ocean water, even in temperate zones, is brutally cold, capable of sapping body heat with terrifying speed. If recovery is delayed by weather, mechanical issues with the recovery ships, or an off-course landing, astronauts bobbing in the ocean could face a life-threatening drop in core body temperature long before their rescuers arrive. This is why rescue forces are stationed across the globe, ready to scramble at a moment's notice, because the safety of the crew is not guaranteed until they are physically pulled from the water and onto the deck of a ship. While an ocean landing is fraught with elemental chaos, landing on a world with no oceans at all presents an even greater engineering puzzle, one that requires a sequence of events so precisely choreographed that it defies belief. The Martian atmosphere is only 1% as dense as Earth's, making it far too thin to slow a heavy lander effectively with parachutes alone, yet just thick enough to create destabilizing turbulence. This impossible set of conditions forced engineers at NASA, a jet propulsion laboratory, to invent an entirely new landing technique for the Curiosity and Perseverance rovers, the audacious sky crane maneuver. This is not a gentle descent, it is a multi-stage, high-stakes ballet of destruction and precision that has been aptly described as 7 minutes of terror. The process begins with a heat shield enduring a blistering entry, followed by a massive supersonic parachute deploying at the exact right moment to bleed off more speed. But the parachute alone is not enough. About a mile above the Martian surface, the lander is still falling at nearly 200 miles per hour. At this critical juncture, the descent stage, a rocket-powered platform, fires its engines to bring the vehicle to a near hover. Then, in a move that seems to defy all conventional wisdom, the sky crane lowers the precious rover on 3 nylon tethers like a spider lowering itself on a thread. For a tense handful of seconds, the 1-ton robot dangles and swings beneath the rocket-propelled jetpack, a configuration that is inherently unstable. The descent stage must simultaneously manage its own thrust to avoid crashing into the rover while paying out the bridle until the rover's wheels make contact with the soil. The instant onboard sensors confirm a stable touchdown. Pyrotechnic charges fire, severing the connecting cables, and the descent stage flies away to crash at a safe distance. A single error in the millions of lines of code, a sensor failure, or a timing discrepancy of just a fraction of a second would send the descent stage crashing down on top of the rover or cause it to release the rover from too great a height, dooming a billion-dollar mission to destruction on the dusty plains of Mars. Whether it's battling the capricious waves of an earthly ocean or relying on a rocket-powered crane to set down gently on an alien world, the conclusion of a space mission is a period of extreme vulnerability. It underscores a humbling truth of space exploration. Leaving a planet is a triumph of power, but returning to one is a masterpiece of control. After surviving the profound emptiness of space, explorers must once again contend with the stubborn, chaotic, and often violent physics of a world with a solid surface. A final, brutal reminder that the safety of home is something that must be earned, not simply returned to. After navigating the fiery terror of re-entry and the violent uncertainty of landing, an astronaut's survival ultimately depends on the one thing that has kept them alive from the very beginning: the mechanical integrity of their spacecraft. This brings us to the 14th danger, a category of threat so vast it encompasses nearly every aspect of the mission: the ever-present risk of catastrophic spacecraft system failure. A spaceship is not a single machine. It is a fragile, interconnected web of thousands of critical systems, each one a potential single point of failure in an environment that offers no second chances. In the void, there is no pulling over to the shoulder, no calling for a tow truck, and no running to the hardware store for a spare part. Every hum, every beep, and every gauge reading represents a system that must function flawlessly, often for years on end, under conditions of extreme stress that would cause ordinary machinery to grind to a halt in moments. The foundational principle for managing this inherent vulnerability is redundancy, a design philosophy that is both a lifesaver and a heavy burden. Engineers build spacecraft with multiple, independent backups for virtually every critical system. There are multiple flight computers that constantly check each other's work, ready to take over in a millisecond if one fails. There are separate power buses so that a short circuit in one doesn't plunge the entire vehicle into darkness. There are arrays of thrusters, so the loss of one or two doesn't mean the crew loses the ability to control their orientation or trajectory. This layered safety net is essential, but it comes at a tremendous cost in weight, complexity, and power. Every redundant system is more mass that the tyranny of the rocket equation forces you to pay for, and more complexity that can, ironically, create new and unexpected failure modes of its own. The spacecraft becomes a tangled ecosystem of primary systems, secondary systems, and sometimes even tertiary backups, all competing for space and resources. A high-stakes testament to the old engineering adage that if you think perfect reliability is expensive, you should consider the cost of failure. To understand how these failures can unfold, we need to move from abstract principles to specific, terrifying possibilities. Imagine a simple valve, one of hundreds controlling the flow of fuel, coolant, or air. In the extreme temperatures and vibrations of space, a microscopic piece of debris could lodge in it, or a seal could harden and fail, leaving it stuck either open or closed. A stuck valve in a cooling loop could allow a critical computer to overheat and shut down, or cause a cabin temperature to skyrocket. A software glitch, a single errant line of code buried in millions, could miscommand a thruster fire at the wrong moment, sending the spacecraft into an uncontrollable spin or wasting precious fuel needed for the return journey. Or consider a power bus failure. The electrical system is the spacecraft's nervous system, and a sudden spike or a failed regulator can cripple it. Lights, computers, life support, communication, everything that makes the vessel habitable and controllable vanishes into silence, leaving the crew floating in a dark, freezing, and dying shell, their only hope resting on the swift activation of a backup system that may or may not function as designed. No story better exemplifies the reality of cascading system failures and the human ingenuity required to overcome them than the harrowing tale of Apollo 13. The mission was proceeding smoothly until a routine stir of an oxygen tank caused damaged wiring inside to short circuit. This single point of failure triggered an explosion that was not just a simple breakdown, it was a chain reaction of disaster. The explosion blew off a whole panel of the service module, crippling one oxygen tank entirely and causing a second to slowly leak its contents into space. Without oxygen, the fuel cells that provided most of the spacecraft's electricity and drinking water also failed. In a matter of minutes, the command module, Odyssey, transformed from a sophisticated spaceship into a lifeless, powerless hulk. The crew was forced to abandon it and use the lunar module, Aquarius, as an improvised lifeboat, a craft designed to support 2 people for 2 days on the surface of the Moon, not 3 people for 4 days in the depths of space. What followed was a masterpiece of real-time, remote troubleshooting, a collaboration between the calm, resourceful crew and the brilliant, frantic teams on the ground. The astronauts became mechanics, working with duct tape, plastic bags, and the very instruction manuals they helped write, to build improvised solutions for problems no one had ever anticipated. They had to figure out how to make the square carbon dioxide scrubbers from the command module work in the round holes of the lunar module system, using only the miscellaneous items they had on board to avoid being poisoned by their own exhaled breath. They had to perform a critical engine burn using the lunar module's descent engine, a motor never intended for this purpose, to adjust their trajectory and slingshot them around the Moon and back toward Earth, all while conserving every amp of power and every drop of water. Apollo 13 stands as the ultimate testament to the fact that in space, the crew must be their own rescue team. It underscores that while redundancy can save you from a single failure, it is human courage, creativity, and an encyclopedic knowledge of your own machine that saves you when multiple systems fail in ways the designers never imagined. The success of that failure redefined spaceflight, teaching a generation of engineers and astronauts that the most important system on any spacecraft is not made of wires or metal, but of flesh, blood, and an unbreakable will to solve the impossible. Of all the potential system failures, perhaps none is more viscerally terrifying than the outbreak of fire within the sealed, oxygen-rich confines of a spacecraft. This is a danger that transforms our most fundamental tool for survival, the controlled environment, into a death trap. Fire on Earth is dangerous enough, but in the microgravity of space, it becomes an alien and deceptive predator, behaving in ways that defy all our terrestrial instincts. Without gravity, there is no buoyancy to carry hot air upward. Flames do not taper and flicker. Instead, they form lethargic, eerie spheres of blue and yellow that hover around their fuel source, consuming oxygen from all directions and radiating heat in a much more efficient and deadly manner. This spherical burning allows fire to wrap itself entirely around objects and creep into corners and crevices that would be safe on Earth, smoldering invisibly within insulation or behind panels, only to erupt again when fresh air circulates. The immediate, dual-pronged threat of any fire is asphyxiation and poisoning. A blaze consumes the spacecraft's precious, finite oxygen at an alarming rate, rapidly creating a hypoxic environment that would starve the crew of breathable air. But long before the oxygen is fully depleted, the real killer emerges, the toxic cocktail of gases produced by combustion. In a spacecraft, almost everything is synthetic: plastics, polymers, composites, and electrical insulation. When these materials burn, they release a horrifying array of poisons, including cyanide gas from certain plastics and carbon monoxide from incomplete combustion. These toxins fill the enclosed volume with no way to vent them, creating an atmosphere that is utterly unbreathable within minutes. You cannot simply open a window to clear the smoke. The only option is to fight the fire immediately and hope the environmental system can scrub the poisoned air faster than the fire is polluting it. This nightmare scenario is not just a theoretical risk. It was a brutal, tragic reality for the Apollo 1 crew during a routine ground test on January 27, 1967. Astronauts Gus Grissom, Ed White, and Roger Chaffee were seated in their command module, conducting a plugs-out test on the launch pad, when a stray electrical spark from faulty wiring ignited the pure oxygen atmosphere inside the cabin. In such a high-pressure, 100% oxygen environment, the fire spread with explosive speed. Flames engulfed the cabin interior almost instantly, and the crew was unable to open the complex, inward-opening hatch against the tremendous pressure built up inside. They perished in a matter of seconds, trapped inside their own spacecraft. The disaster was a watershed moment for NASA, forcing a complete redesign of the command module with a safer, mixed-gas atmosphere, flammable materials replaced with self-extinguishing alternatives, and a hatch that could be opened explosively from the inside in less than 10 seconds. The deaths of the Apollo 1 crew serve as a permanent, sobering memorial to the fact that the danger of fire is ever present, and that the consequence of even a minor oversight can be absolute. In response to this perpetual threat, modern spacecraft like the International Space Station are equipped with specialized firefighting tools and protocols. Instead of water, which would form floating, uncontrollable globules that could short out electrical systems, crews rely on portable fire extinguishers that emit a fine mist or a jet of carbon dioxide to smother the flames by displacing oxygen. Every crew member undergoes rigorous training, drilling for fire emergencies where they must quickly don oxygen masks, locate the source using smoke detectors, and extinguish the blaze while communicating with their crewmates and mission control. Yet, for all this preparation, the terrifying truth remains that a major, rapidly spreading fire represents one of the few truly unsurvivable events in spaceflight. On a long-duration mission, far from any hope of rescue, a fire that compromises the primary life support systems or creates an atmosphere too toxic to scrub would mean there is no way out. The spacecraft, designed to be a protective shell against the void, would become a sealed tomb, a stark and horrifying reminder that some of the most profound dangers in space are not outside the hull but locked inside with you. But even with all the redundancy and firefighting protocols in the world, there exists a scenario so chilling it represents the absolute finality of space exploration's risks. This is the 16th danger, the ultimate nightmare of a permanent, unsolvable failure. The loss of a mission leading to the marooning of a crew, left adrift in the void or stranded on an alien world with no conceivable path home. It is the point where every other danger converges into a single, inescapable outcome, transforming a vessel of exploration into a floating tomb or a desolate outpost on a dead world, with the crew fully aware of their fate. The psychological weight of this knowledge is a terror unlike any other, a slow-motion countdown where hope itself becomes the enemy. the immediate horror is not the failure itself, but the dawning comprehension of its finality. For a crew in orbit around Earth, a catastrophic engine failure or a massive power loss could leave them trapped, circling the planet in a slowly dying craft. They would watch their homeworld, beautiful and vibrant, pass by their window again and again, a constant, torturous reminder of everything that is now permanently out of reach. The frantic efforts of ground control would gradually turn from rescue planning to managing the inevitable, as the grim logistics of limited resources take center stage. Every breath depletes the remaining oxygen. Every sip of water brings the dry tanks closer to empty. The crew would be forced to make unbearable decisions, potentially rationing supplies or even powering down non-critical systems to extend their consciousness for a few more hours or days, all while knowing it only prolongs the anguish. This is not a quick end. It is an existential crisis stretched over a timeline measured in the remaining kilowatts and cubic feet of air. This terrifying premise was brought to life with remarkable scientific accuracy and grim wit in Andy Weir's The Martian, where astronaut Mark Watney is stranded on Mars after his crew believes he has been killed. The story brilliantly illustrates the sheer, relentless problem-solving required to survive against impossible odds. Watney becomes a master of improvisation, growing food in a habitat never designed for agriculture, manufacturing water from rocket fuel, and even repurposing a nuclear-powered rover for a desperate cross-planet journey. His story is a tribute to human ingenuity, but it's crucial to recognize it as a work of fiction that glosses over the bleakest realities. For instance, Watney never truly faces a life support failure he cannot fix, a radiation event that sickens him, or a psychological breakdown from the utter, soul-crushing loneliness of being the only person on an entire planet. The novel's optimism, while inspiring, masks the overwhelming probability that a single, second major failure would have ended his story for good. And this leads to the most sobering truth of our current era of space exploration. For any mission venturing beyond the moon, there is no rescue capability. There is no second spacecraft waiting on standby for a trip to Mars. There is no ability to mount an emergency supply run. A crew sent on a multi-year journey to the Red Planet is embarking on a voyage of no return until the predetermined launch window for their journey home opens years later. They are utterly on their own. This fundamental isolation makes the design of mission abort options and layered redundancies not just an engineering priority, but a moral imperative. Every system must be analyzed not only for how it can fail, but for how its failure could strand the crew. The concept of safe haven becomes critical, ensuring that if one module is compromised, the crew can retreat to another that can sustain them indefinitely. But for a Mars mission, the habitable space is the entire spacecraft. There is no backup planet to retreat to. A failure that compromises the vehicle's ability to leave Mars' orbit or to produce food and water for the return journey is a death sentence delivered with cold, mathematical certainty across millions of miles of empty space. This ultimate danger forces us to confront a profound ethical question, underscoring that the courage to explore must be matched by an unwavering commitment to never, ever leave our explorers behind. And yet, the body's adaptations to this gravity-free world extend far beyond the weakening of our frame, striking at the very core of our life-sustaining systems. The 17th danger is a quiet, internal revolution against the cardiovascular system, the intricate network that has spent your entire life in a constant, silent battle against Earth's pull. In weightlessness, that primary opponent simply vanishes, and the consequences are both immediate and profound. The heart, a powerful muscle that has always worked to push blood upward against gravity, suddenly finds its job has become almost laughably easy. Without that constant resistance, it begins to adapt with a ruthless efficiency, becoming less fit, weaker, and physically smaller, a condition known as cardiac atrophy. Think of it like a weightlifter who stops going to the gym. The muscle doesn't just maintain its strength, it actively shrinks because the body sees no need to sustain what it isn't using. For an astronaut, this isn't just a matter of fitness, it's a fundamental change to the organ that keeps them alive, raising serious questions about its ability to handle the sudden return of gravitational stress or to perform under the physical demands of an emergency on a distant world. This cardiac deconditioning is powerfully exacerbated by a bizarre and pervasive phenomenon we touched on earlier, but which has even deeper implications for cardiovascular health: the dramatic fluid shift. On Earth, gravity pulls roughly 2 liters of fluid, blood and other liquids down into your legs and lower torso. Your entire circulatory system, from the powerful heart to the one-way valves in your veins, is engineered to fight this pull, working constantly to return that blood to your brain and upper body. The moment you enter microgravity, that struggle is over. The fluid, no longer held down, drifts upward into the chest and head. This is what causes the classic astronaut appearance of puffy face bird legs, a round, flushed face accompanied by noticeably thinner legs as the fluid vacates the lower extremities. But this isn't just a cosmetic change, it's a systemic shock. The body's sensors, located in the heart and neck, misinterpret this new, constant volume of fluid in the upper body as a sign of chronic overhydration. Believing the entire system is flooded, the body triggers a response to excrete the excess, leading to a rapid loss of fluid and electrolytes. Within the first day or two in space, an astronaut can lose up to 10% of the fluid from their bloodstream. It's a brilliant, if misguided, adaptation to a new environment, but one that sets the stage for a crippling problem upon the return to a world with a downward pull. The most direct and dangerous consequence of this entire process manifests the moment an astronaut tries to stand up back on Earth, a condition called orthostatic intolerance. After months in space, the body has completely recalibrated itself for a gravity-free existence. The heart has shrunk and grown accustomed to a lower workload. The blood volume is reduced, and the reflexes that quickly constrict blood vessels in the legs to prevent blood from pooling there have become lazy and unresponsive. When the crew lands and is once again subjected to gravity, the system is utterly unprepared. As they move to an upright position, blood immediately rushes downward, pooling in their legs and abdomen. The shrunken, deconditioned heart struggles to pump strongly enough to overcome this pooling and push sufficient blood back up to the brain. The body's delayed vascular response is too little, too late. The result is a sudden, dramatic drop in blood pressure to the brain, leading to dizziness, graying vision, ringing in the ears, and in many cases a full faint. They literally fall over because their bodies have forgotten how to stand. Managing this cardiovascular crisis is a critical part of any return mission. Astronauts are carefully extracted from their capsules and placed in recliners to minimize the strain of standing. They are encouraged to drink saline solutions to quickly rebuild their blood plasma volume, and they often wear compression garments on their lower bodies to mechanically counteract the blood pooling. The rehabilitation process is slow and deliberate, involving tilt table exercises that gradually re-acclimate the body to gravitational stress. This systemic deconditioning presents a monumental hurdle for future missions to Mars. Imagine an explorer, after a grueling 9-month journey in microgravity, finally landing on the red planet. Their first task would be to don a heavy, cumbersome spacesuit and step out onto a new world. But if their cardiovascular system cannot support them in a simple standing position on Earth, how could it possibly handle the physical exertion of Martian exploration, even in its lighter gravity? They could arrive as heroes only to be confined to their habitat, too dizzy and weak to take their first historic steps, their bodies betrayed by a heart that adapted too well to the freedom of the void. Now we delve into a danger that operates like a silent saboteur, undermining an astronaut's health from within: the alarming and systematic weakening of the human immune system. After adapting to fluid shifts and muscle atrophy, the body now faces a threat from its own internal defenses, which appear to become confused and sluggish in the alien environment of space. Extensive research has revealed a deeply concerning pattern. Many of the vital cells and signaling pathways that constitute our immune surveillance network simply do not function with their usual vigor in microgravity. Key defender cells such as T cells and natural killer cells, which are supposed to rapidly identify and destroy infected or cancerous cells, show a marked reduction in their effectiveness. They become slower to activate and less lethal in their response, essentially leaving the body more vulnerable to threats it would normally handle with ease. It's as if the body's entire security force has been put on a reduced alert status, creating a dangerous gap in its biological defenses just when an astronaut needs them most. This immunosuppression isn't just a theoretical concern confined to Petri dishes. It manifests in very tangible and personal ways for crew members. One of the most well-documented effects is the reactivation of latent viruses that have been dormant in an astronaut's body for years, sometimes since childhood. The virus responsible for chickenpox, for example, can reawaken in the form of shingles, causing painful skin lesions. Other common culprits include the Epstein-Barr virus and herpes simplex, which can resurface without the usual robust immune response to keep them in check. Astronauts frequently show elevated levels of these viruses in their saliva and other bodily fluids, a clear biological signal that their internal watchdogs are napping. This means that a crew member could spend a mission not only fighting the external challenges of space, but also battling a viral enemy from their own past, all while their body is less equipped to mount a proper defense. Scientists point to a confluence of factors that create this perfect immunological storm. The immense chronic stress of spaceflight is a prime suspect. The combination of radiation exposure, the psychological strain of confinement and isolation, the disruption of circadian rhythms from multiple sunrises and sunsets each day, and even the high-intensity physical and mental workload all contribute to elevated levels of stress hormones like cortisol. Cortisol is a potent anti-inflammatory agent, and in sustained high doses, it can broadly suppress immune activity, telling the body's defense systems to stand down. This stress-induced suppression is similar to what we observe in highly stressed individuals on Earth, but it is magnified by the unique conditions of space. Furthermore, the strange fluid shifts we discussed earlier may also play a role, potentially altering the very environments where immune cells are produced and mature, like the bone marrow, further disrupting the body's ability to generate a fully functional army of defenders. But the danger is compounded by a startling twist. While the human immune system is weakening, the microbes we carry with us seem to thrive and become more formidable. Bacteria like Salmonella and Pseudomonas have been shown to become more virulent and resistant to antibiotics when cultured in microgravity. In the low-shear, fluid dynamic environment of space, these microbes alter their gene expression, developing thicker protective capsules and forming robust, slimy communities called biofilms that are notoriously difficult for both the immune system and antibiotics to penetrate. This means the confined environment of a spacecraft, which is teeming with microbes from the crew and their surroundings, becomes a potential petri dish of supercharged pathogens. An astronaut with a dampened immune system is therefore sharing a small, sealed volume with bacteria that have become better equipped to cause a serious infection. A simple scratch, a minor sinus infection, or a case of food poisoning that would be a nuisance on Earth could escalate into a mission-critical medical emergency hundreds of miles above the planet, with only limited medical resources and no possibility of a quick evacuation to a hospital. This precarious balance between a weakened host and empowered microbes represents one of the most complex and insidious biomedical challenges we must solve for the future of long-duration spaceflight. Returning now to the silent menace of orbital debris, we find a danger that has evolved from a theoretical concern into a clear and present emergency, a ticking time bomb in the space above us. The numbers themselves tell a story of exponential risk. As of today, the official catalogue of trackable objects, those larger than a softball, has swelled to well over 30,000. But this is merely the tip of the iceberg. Lurking just below this threshold of observability are an estimated 1 million fragments between the size of a marble and a softball, any one of which could deliver a knockout blow to a satellite or crewed vehicle. And then there are the ghosts, the hundreds of millions of paint flecks and minuscule shards, untrackable with current technology, yet traveling at 17,500 miles per hour, each one possessing enough kinetic energy to crack a window or disable a critical sensor. What was once a vast, open frontier is rapidly becoming a celestial graveyard of our own making, a congested orbital highway where every crossing carries the risk of a catastrophic collision. This spiraling crisis is a textbook example of what economists and ecologists call the tragedy of the commons, playing out on a global scale. The orbital space around Earth is a shared resource, a commons that belongs to no single nation but from which every spacefaring country benefits. The problem is that the incentives for individual actors are misaligned with the collective good. For a private company launching a mega constellation of thousands of internet satellites, the cheapest and easiest option at the end of a satellite's life is to simply leave it in orbit or to deorbit it in a way that might take decades. The cost of that inaction, the increased risk to all other spacecraft, is distributed across the entire international community, while the savings are reaped by the single company. This creates a classic free rider problem where everyone relies on everyone else to be responsible, but no one is fully accountable for the mess they create. It's a high-stakes game of orbital chicken where the penalty for collective failure is not just the loss of a few satellites, but the potential sealing off of entire orbital pathways for generations. Recognizing the precipice we are approaching, a global scramble for solutions is now underway, though the scale of the challenge is truly daunting. On the regulatory front, international guidelines, such as those from the Inter-Agency Space Debris Coordination Committee, now recommend that operators ensure their satellites deorbit within 25 years of mission completion. While a step in the right direction, this time frame is still dangerously long, and these guidelines are just that, guidelines, not enforceable laws. More promising are the technological solutions now moving from the drawing board to reality. Several companies and agencies are actively testing debris removal concepts. These range from missions like Clear Space, which plans to use a giant robotic claw to capture a defunct payload adapter, to experimental systems that employ harpoons, nets, or even powerful lasers to nudge debris into faster decaying orbits. The European Space Agency's forthcoming mission is a critical proof of concept, aiming to demonstrate that we can actively clean up our celestial backyard. Yet, these are still small-scale demonstrations targeting a handful of large objects. The monumental task of dealing with the hundreds of thousands of smaller, yet equally lethal, fragments remains largely unaddressed, a cleanup operation of almost unimaginable complexity. This leads to the haunting and very real possibility that our efforts, however well-intentioned, may be arriving too late. The most terrifying scenario remains the Kessler syndrome, a cascading chain reaction of collisions we discussed earlier. With the sheer density of objects now in low Earth orbit, some experts fear we may be approaching a critical tipping point where one major collision could trigger an unstoppable domino effect. Imagine a single collision between an old rocket body and a defunct satellite, shattering both into 10,000 new pieces. Each of those pieces becomes a new projectile, dramatically increasing the probability of the next collision, which creates even more debris, and so on. The result could be an impenetrable shell of shrapnel encircling our planet, a swirling vortex of metal that would render low Earth orbit unusable. Satellites for weather forecasting, global communications, disaster management, and GPS would be systematically pulverized, setting our technologically dependent civilization back by decades. Crewed missions to the Moon or Mars would become impossibly dangerous, as spacecraft would have to navigate a minefield just to leave their home planet. The dream of space exploration could be put on hold for a century or more, not because we lacked the ambition, but because we failed to take out the cosmic trash. The decisions we make in the next decade to enforce stricter regulations, fund active debris removal, and prioritize long-term sustainability over short-term profit will determine whether the space above Earth remains a gateway to the stars or becomes our species' largest and most tragic junkyard. Consider for a moment that our Sun, the source of all life and warmth for our planet, is also a seething, unstable ball of plasma capable of an apocalyptic temper tantrum. We've already discussed the steady drizzle of cosmic radiation, but that pales in comparison to the sudden solar fury of our 20th danger, the colossal explosions known as solar flares and coronal mass ejections. A solar flare is a flash of intense, high-energy radiation across the electromagnetic spectrum, from radio waves to powerful X-rays and gamma rays. It's a burst of light that travels at the speed of light, reaching Earth or a spacecraft in a mere 8 minutes. But while that flash is dramatic, it's often the opening act for the main event, the coronal mass ejection. Imagine the Sun literally coughing up a piece of its own atmosphere. A CME is a billion-ton cloud of magnetized solar plasma, a roiling storm of protons and electrons hurled into the solar system at speeds that can exceed several million miles per hour. This isn't just radiation, it's a physical, tangible storm of matter, a hurricane of charged particles with its own magnetic field. And if one is aimed directly at a crewed mission, it represents one of the most acute and inescapable threats in all of space exploration. The sheer energy contained within one of these events is almost incomprehensible. A single, large coronal mass ejection can release energy equivalent to millions of 100-megaton nuclear bombs detonating simultaneously. Fortunately for life on Earth, our planet comes equipped with a powerful, global-scale defense system. Our magnetic field acts as a protective bubble, deflecting the vast majority of these charged particles. The ones that do get funneled toward the poles create the beautiful auroras, a harmless light show from an otherwise violent encounter. Our thick atmosphere then absorbs any remaining radiation, ensuring the storm never reaches the surface. But for astronauts anywhere beyond this protective cocoon, the situation is dire. On the Moon, with no global magnetic field and only the barest wisp of an atmosphere, an astronaut caught on a surface walk during a major solar storm would receive a lethal dose of radiation in a matter of hours. On Mars, the situation is slightly better but still perilous. The planet has a very weak magnetic field and a thin atmosphere, offering only a fraction of the protection we enjoy on Earth. A crew on the Martian surface might have slightly more time to react, but they would still be in a race against an invisible, deadly tide. This creates a frantic, high-stakes scramble for survival, a concept that mission planners refer to as the storm shelter. Since a spacecraft's standard aluminum hull offers negligible protection against the intense proton bombardment of a solar storm, crews must retreat to a specially designed, heavily shielded compartment. Often, this shelter is a small area of the spacecraft, like a crew quarters or a storage bay, whose walls are lined with the densest materials available. In many designs, this shielding is provided by the astronauts' own, supplies bags of water, food, and even their own waste, all of which are rich in hydrogen atoms that are exceptionally effective at blocking this type of particle radiation. The crew would huddle in this cramped makeshift bunker, perhaps for 24 hours or more, waiting for the storm to pass. It's a claustrophobic and psychologically taxing ordeal, a period of forced inactivity and heightened anxiety, knowing that a wall of energetic particles is sleeting through the rest of their ship, potentially damaging electronics and delivering a radiation dose that, while survivable inside the shelter, would be fatal just a few feet away. Yet for all our planning, the terrifying reality is that our current technology offers no surefire defense against a truly extreme solar storm. History provides a chilling precedent, the Carrington event of 1859. A coronal mass ejection of that magnitude, if it were to strike Earth directly today, would cause catastrophic damage to our power grids and satellites. Now imagine that same titanic force hitting a spacecraft en route to Mars. A direct hit from a Carrington-class event could overwhelm even the best storm shelter. The radiation levels inside the craft could spike to unsurvivable levels, and the intense electromagnetic pulse and particle shower would almost certainly fry critical, unshielded avionics, leaving the vehicle dead in the water, or rather dead in the void. The spacecraft's computers, navigation, and communication systems would be reduced to useless silicon, stranding the crew in interplanetary space without power, without guidance, and without any hope of recovery. In such a scenario, the mission would not just fail, it would end in the most tragic way imaginable, with the astronauts fully conscious and aware of their fate as their systems slowly died around them. This ultimate vulnerability underscores a harsh truth. As we venture farther from Earth, we are trading the comprehensive protection of our home world for a fragile, manufactured shell, one that could be pierced in an instant by the random, violent whims of our own star. And just when you think you have mastered the physics of spaceflight, a different kind of barrier emerges, one that separates you not by distance but by time itself. This is the 21st danger, a deep and unnerving silence imposed not by equipment failure, but by the unchangeable laws of the universe. We are talking about the perilous reality of communication lag and blackouts, a challenge that transforms the very nature of mission control from a real-time partner into a distant advisor, and turns moments of crisis into exercises in terrifying solitude. The most profound manifestation of this is the simple, brutal delay that grows with every mile traveled from Earth. For astronauts in low Earth orbit, chatting with mission control in Houston is almost like a phone call with a delay of less than a second. But venture out to the Moon and that delay stretches to a few seconds. Now push onward to Mars and the lag becomes a chasm. Depending on the ever-changing positions of the two planets in their orbits, a radio signal traveling at the speed of light can take anywhere from 4 to 24 minutes for a one-way trip. That means a simple question from an astronaut on Mars: "Houston, we have an alarm on the life support system. What do you see?" would take 20 minutes to reach Earth. The answer from a frantic engineer: "Check valve 7 alpha, it's showing a pressure drop," would take another 20 minutes to come back. In those 40 minutes of silence, the crew is completely on their own. A leak could have emptied the cabin, a fire could have started and been put out, or a critical course correction could have been missed. This time lag fundamentally redefines the relationship between the crew and the ground. Mission control can no longer be a real-time pilot. Its role shifts to that of a long-range planning and advisory center, sending up meticulously vetted procedures and contingency plans for the crew to execute autonomously. The astronauts become the true captains of their vessel, forced to make split-second decisions without any possibility of consultation, carrying the entire weight of the mission on their shoulders in a way no human in history ever has. This chronic communication delay is difficult enough, but it is punctuated by an even more intense, though planned, period of total silence, the re-entry blackout. As a spacecraft like Orion or a Crew Dragon slams back into Earth's atmosphere at 25 times the speed of sound, it compresses the air in front of it into a seething plasma of ionized particles. This superheated gas, which creates the fiery glow of re-entry, also has a peculiar property. It is an excellent reflector of radio waves. For a period of several minutes, the capsule is completely enveloped in this electrically charged shroud, which acts like a mirror, blocking all radio signals from escaping or entering. To mission control, the crew simply vanishes from the airwaves, the telemetry data. The heartbeat of the spacecraft cuts out abruptly, and the voice channel falls into an unnerving static. This blackout is a calculated part of every return, but that doesn't make it any less harrowing. Everyone in the control room knows the spacecraft is enduring temperatures of 3,000 degrees Fahrenheit and experiencing G-forces that can push the limits of human tolerance. They know the heat shield is being put to the ultimate test, but for those few minutes they are utterly blind and deaf, forced to simply wait and trust the engineering. They stare at their silent consoles, hoping and praying that their friends will emerge from the fire on the other side. The psychological toll of this enforced isolation, both the chronic lag and the acute blackout, cannot be overstated. For the crew, the re-entry blackout is the final, silent trial after a long journey. They are hurtling through a tunnel of fire, fully aware that if anything has gone wrong, there is no way to call for help and no way for help to reach them. They must ride out the storm in faith. For the families watching and the controllers waiting, it is an agonizing exercise in powerlessness. The history of spaceflight is filled with the palpable tension of these moments. During the Apollo missions, the blackout period was always the most silent and tense part of the control room. Every second of expected blackout that passed without a signal was a lifetime. The moment the first crackle of a voice broke through the static, "Houston, this is Odyssey, do you copy?" was always met with an explosive release of relief and cheers. But this dynamic also highlights a terrifying vulnerability. If a genuine, unexpected emergency were to occur during the blackout period, a parachute failure, a sudden cabin depressurization, the crew would face it in complete radio silence. Their final moments, their attempts to solve the unsolvable, would be theirs alone, with no one on the ground ever hearing their struggle. It is one of the most profound and chilling realities of space travel, a reminder that at the most critical junctures the connection to home is severed, and explorers must face the abyss with only their own courage and preparation to guide them. Beyond the well-known risk of cancer, radiation in deep space carries a more insidious and immediate threat to the very organ that defines an astronaut's ability to function, the brain. We have discussed the intense solar storms that demand a retreat to a storm shelter, but the real psychological menace comes from a quieter, more persistent source. Galactic cosmic rays, those atomic nuclei fired from distant supernova, are a constant, high-energy drizzle that cannot be shielded against with any practicality. Unlike the protons from a solar event, these are heavy ions. Think iron and silicon traveling at nearly the speed of light. When one of these microscopic bullets tears through a spacecraft's hull, it doesn't just stop, it creates a secondary spray of shattered particles. And when that cascade passes through the delicate, complex architecture of the human brain, the effects are both deeply troubling and bizarrely perceptible. The damage is not merely a matter of increased future risk, it is a form of real-time physical trauma. As these high atomic number particles rip through brain tissue, they act like microscopic cannonballs, severing neural pathways, damaging the protective sheathing around nerve fibers, and triggering widespread inflammation. The brain's remarkable plasticity can repair some of this damage, but the assault is relentless. The most chilling evidence comes from animal studies conducted here on Earth, where scientists simulate space radiation by exposing lab mice to similar heavy ions. The results are sobering. These animals show clear and persistent signs of cognitive decline. They become worse at navigating mazes, have difficulty recognizing novel objects, and display signs of anxiety and impaired judgment. They are, in essence, experiencing accelerated brain aging. For an astronaut on a 3-year mission to Mars, this could translate into a gradual erosion of the skills they need most. The ability to make split-second decisions during an emergency, to perform complex, multi-step repairs, or to maintain sharp focus during long, monotonous stretches of the journey. An astronaut might find their memory becoming less reliable or their reaction times slowing at the very moment a crisis demands peak mental performance. Perhaps the most unnerving aspect of this radiation is that astronauts are sometimes directly aware of its passage through their heads. With their eyes closed in the dark quiet of their sleep station, many have reported experiencing sudden, vivid visual flashes. These are not dreams or hallucinations in the traditional sense. They are described as sudden streaks of light, starbursts, or fleeting geometric patterns, completely disconnected from any external light source. Scientists have confirmed that these phantom lights are caused by individual cosmic rays or their secondary particles striking the retina or directly stimulating the visual cortex. It is the human nervous system interpreting a violent subatomic collision as a flash of light, a tiny, personal firework display signaling a direct hit. While not physically painful, this phenomenon serves as a constant, low-level reminder of the invisible barrage they are enduring, a sensory confirmation that their brain is literally under fire from the galaxy itself. All of this paints a deeply worrying picture for the future of interplanetary travel. While we can design storm shelters to protect against the predictable fury of the sun, there is no such refuge from the galactic cosmic rays. They are a permanent feature of the deep space environment, and our current spacecraft materials, like aluminum, are not just inadequate, they can make the problem worse by generating more secondary particles upon impact. The solution may lie in developing entirely new shielding materials rich in hydrogen, such as polyethylene or water, which are more effective at blocking these heavy ions without creating as much secondary shrapnel. Some concepts even imagine lining the crew's sleeping quarters with their own water supply, creating a protective cocoon for the brain during sleep. But for now, these are largely concepts. The stark reality is that we are contemplating sending explorers on the most ambitious voyage in human history without a clear solution to a danger that could fundamentally and permanently alter their cognitive abilities, turning the journey of a lifetime into a potential threat to their very identity. Now, layer upon the psychological and physiological challenges we have explored. Consider a danger so fundamental we often take it for granted here on Earth, the simple, vital act of eating. This 23rd peril, the struggle for nutrition and food security in space, transforms one of life's greatest pleasures into a complex logistical puzzle and a potential point of catastrophic failure. In the sterile, weightless environment of a spacecraft, the very experience of eating is stripped of its sensory richness. With no gravity to pull fluids downward, an astronaut's body experiences that constant fluid shift we discussed, leading to chronic sinus congestion not unlike a permanent head cold. This congestion dramatically dampens the sense of smell, which is intrinsically linked to our ability to taste. Combine that with the lingering background odors of the spacecraft itself, a mix of machine oil, recycled air, and plastics, and you have a recipe for a profound loss of appetite. Food that was carefully crafted and packaged on Earth suddenly tastes bland, metallic, or simply unappealing. When nothing tastes good, the motivation to eat withers. An astronaut might push away a meal not out of stubbornness, but because their own biology is telling them they are not hungry. Over a 6-month mission, this consistent undereating can lead to unhealthy weight loss, muscle wasting, and a dangerous lack of essential vitamins and minerals, weakening the crew for the physical demands of their mission and their eventual return to gravity. This sensory challenge forces space agencies to become culinary innovators, constantly searching for ways to make food palatable and appealing. The famous image of astronauts squeezing pureed meals from toothpaste-like tubes is a relic of the past. Today's menus on the International Space Station are far more varied, featuring thermostabilized, irradiated, and rehydratable foods, from scrambled eggs and beef tips to even the occasional slice of pizza. Seasoning is key, but not in the form of loose salt and pepper, which would float away and clog air vents. Instead, astronauts use liquid saltwater and pepper solutions. Despite these efforts, the monotony of the menu is a persistent foe. Imagine eating the same 100 or so pre-packaged meals for months on end, with no access to a fresh salad, a piece of fruit, or a home-cooked meal. This culinary tedium further erodes the social and psychological benefits of sharing a meal, turning a daily ritual of comfort into just another item on the checklist. Given these limitations, the logical next step seems to be growing food in space, creating a self-sustaining bioregenerative life support system. This ambition, however, collides with the brutal realities of the space environment. Plants, like humans, did not evolve for microgravity. Their root systems, which rely on gravity to know which way to grow, become disoriented. Water does not percolate down through soil. Instead, it forms floating blobs that can drown roots or drift away, leaving them desiccated. To solve this, engineers have developed sophisticated hydroponic and aeroponic systems, where a nutrient-rich mist is sprayed directly onto the roots in an enclosed chamber. Light is provided by specially tuned LED arrays, since natural sunlight is unavailable on a spacecraft and arrives in punishing, unfiltered bursts outside. But then there is radiation. While plants on Earth are shielded by our atmosphere and magnetic field, crops in space are bombarded by the same galactic cosmic rays and solar particles that threaten astronauts. This radiation can cause genetic mutations in the plants, stunting their growth, reducing their yield, or rendering them inedible. Successfully growing a small crop of lettuce on the space station is a monumental achievement, but it is a far cry from producing the volume and variety of calories needed to sustain a crew for years. This brings us to the ultimate, gut-wrenching nightmare scenario for any long-duration mission: the complete loss or contamination of the food supply. On a journey to Mars, there are no emergency resupply ships. The entire nutritional requirement for a crew of 4 for 3 years, amounting to many tons of food, must be launched with them or grown along the way. Now imagine a single point of failure, a malfunction in a storage module's cooling system that spoils half the frozen food, a pervasive mold that contaminates the dry goods, or a catastrophic failure in the hydroponic garden that wipes out the fresh food production. The calculations for these missions are precise and leave almost no room for error. A significant loss of calories would force the crew onto strict, soul-crushing rations long before they ever reached their destination. They would face the slow, grinding agony of starvation while utterly isolated, watching their bodies consume themselves as they drifted further and further into the void. The psychological impact of such a situation would be devastating, turning every meal into a grim reminder of their dwindling resources and potentially leading to conflict and despair. It is a primal fear, one that harks back to the earliest maritime explorers, but with a crucial difference: those sailors could sometimes fish or find land. For a crew between planets, the pantry is all there is, and if it fails, the final frontier becomes a vast and empty dining hall with nothing left on the menu. Even with the most sophisticated machinery and flawless engineering, there remains one unpredictable variable that no amount of testing can ever fully eliminate: the human mind itself. This 24th danger forces us to confront a humbling truth. In an endeavor defined by supercomputers and precision physics, the greatest point of failure can sometimes be the person in the loop. We are talking about the ever-present risk of human error, a peril born from the complex interplay of fatigue, immense stress, and the sheer cognitive overload that comes with managing a miniature world in the void. An astronaut's mind is the mission's most critical CPU, but it is one that runs on sleep, is fueled by morale, and can be compromised by a single moment of misjudgment under crushing pressure. The environmental conditions of spaceflight actively work against peak mental performance. The constant noise of machinery, the disruption of normal sleep-wake cycles due to rapid sunrises and sunsets, and the physical discomfort of weightlessness all contribute to a state of chronic fatigue. Layer onto that the unrelenting psychological stress of knowing that a single mistake could be fatal, and you have a perfect storm for cognitive degradation. This isn't about negligence, it's about the fundamental limits of human endurance. When the brain is tired and stressed, its ability to process complex information, make rapid decisions, and maintain vigilant situational awareness begins to erode. An astronaut might misread a data stream, forget a step in a long and complex procedure, or fail to recognize the early warning signs of a system failure simply because their mental resources are stretched to the breaking point. In an environment where every action is magnified, a tiny lapse in attention can initiate a cascade of consequences. We can see the stark reality of this risk etched into the history of space exploration itself. Consider the Apollo 11 mission, a triumph of human achievement that came within seconds of a potential disaster. As Neil Armstrong and Buzz Aldrin descended toward the lunar surface, their computer began flashing unexpected alarm codes. At the same time, Armstrong realized the autopilot was taking them directly into a football field-sized crater littered with boulders, a completely unsuitable landing site. With fuel reserves critically low and alarms blaring, Armstrong was forced to take manual control. He coolly flew the lunar module horizontally, skimming over the treacherous terrain, searching for a safe spot with just moments of fuel remaining. A less experienced pilot, or one paralyzed by the cognitive overload of the alarms and the looming crash, might have frozen or made a panicked decision. Armstrong's ability to process multiple streams of high-stakes information under extreme duress and execute a perfect manual landing is what saved the mission. It was a triumph of human skill, but it also highlights how close we came to catastrophe because of an unforeseen navigational challenge that required a superhuman level of composure. A different yet equally dangerous type of human error emerges not from a lack of skill, but from an over-reliance on technology. This is the phenomenon of automation complacency. When complex systems function flawlessly for days, weeks, or months on end, the human mind, wired to conserve energy, can begin to disengage. An astronaut monitoring a largely automated spacecraft might transition from active problem solver to a passive observer, their vigilance dulled by the consistent, reassuring hum of the machines. They may start to see what they expect to see on their data displays, glossing over a subtle anomaly that a more actively engaged mind would flag. The danger is that when a true emergency finally does occur, it can take precious seconds or even minutes for the astronaut to shift mental gears from a passive monitoring state back into a high-alert decision-making mode. In a crisis where every second counts, that delay can be the difference between a managed incident and a lost vehicle. This complacency is often compounded by the sheer complexity of the interfaces themselves. Modern spacecraft are controlled through multiple layers of software and intricate display panels. An astronaut must navigate through various software screens to find specific data or activate certain systems. In a high-stress situation, it is entirely possible to select the wrong menu option, misinterpret a confusingly displayed piece of data, or input an incorrect command under pressure. There is no simple undo button. A command sent to fire a thruster or reconfigure a life support parameter is immediate and consequential. The software does what it is told. It cannot intuit the human's intent if the input is wrong. This creates a scenario where the very tools designed to reduce human error can sometimes create new avenues for it, especially when the human operator is fatigued, stressed, or has fallen into a routine of trusting the automation a little too much. In the high-stakes theater of space, the most advanced system of all, the human brain, requires constant nurturing, monitoring, and self-awareness to perform at its peak, because its failures, however rare, can resonate with the force of a cannon in the silent fragility of a spacecraft. It's a sobering realization that after overcoming cosmic radiation, system failures, and the void itself, one of the most formidable threats to space exploration doesn't come from the stars at all, but from the very planet we launch from. This is the 25th danger, the political and economic perils that tether the future of spaceflight to the ever-shifting landscape of earthly priorities. While engineers battle the laws of physics, mission directors must navigate a different kind of unpredictable terrain: the world of government funding, international relations, and public opinion, where a single election or a budget crisis can bring a generation of progress to a screeching halt. The most advanced spacecraft ever conceived is utterly powerless if it remains grounded, not by a technical flaw, but by a lack of money or political will. The vulnerability to funding is a chronic, existential threat. Ambitious space projects operate on timelines that span decades, far longer than the election cycles of the governments that typically fund them. A mission conceived under one administration, with years of research and development already invested, can be suddenly cancelled or drastically scaled back by the next. The infamous case of the Constellation program in the United States serves as a stark lesson. Initiated in 2005 with the goal of returning humans to the Moon and eventually reaching Mars, the program spent billions of dollars and nearly a decade of work developing new rockets and spacecraft like the Ares and Orion. Then, in 2010, a new administration deemed it unsustainable and cancelled it, arguing it was over budget and behind schedule. The human cost was immense, with thousands of highly skilled engineers and scientists losing their jobs, and the technological momentum was shattered. It was like building the foundation and frame of a cathedral, only to have the next architect order it torn down to make room for a different design. This start-stop cycle is incredibly wasteful and demoralizing, stranding brilliant technology as museum pieces and forcing the entire industry to pivot with the political winds, rather than following a steady, long-term compass toward a common goal. Beyond simple cancellation, this political volatility can create intense pressure to rush, leading to unacceptable compromises in safety. When a new space race dynamic emerges, as we are seeing today with multiple nations and private companies vying for lunar access and beyond, the urge to be first can override the imperative to be safe. Political leaders may demand visible, symbolic victories by a certain date, a landing on an anniversary, a flagship mission before an election. This top-down pressure can force engineers to take dangerous shortcuts, skipping rigorous testing phases or waiving safety protocols that were established through bitter experience and blood. We have seen this before. In the lead-up to the Space Shuttle Challenger launch in 1986, engineers from the company that built the solid rocket boosters vehemently opposed the launch due to concerns that the cold temperatures would compromise the critical O-ring seals. Their warnings were overruled by managers who felt immense pressure from NASA to maintain the shuttle's ambitious launch schedule. The result was a catastrophic failure and the loss of 7 lives, a tragedy born not from a lack of engineering knowledge, but from a culture where political and bureaucratic pressure fatally eroded safety margins. Perhaps the most alarming political danger is the escalating drift toward the militarization of space. For decades, space has been largely a realm of peaceful, scientific cooperation, best exemplified by the International Space Station, a partnership between former Cold War adversaries. But as our reliance on space-based assets grows for communication, navigation, intelligence, and military command and control, the temptation to treat orbit as a new battlespace becomes stronger. Nations are now developing and testing anti-satellite weapons, which we've already seen can create devastating clouds of debris that threaten every spacecraft in a given orbital shell. The logical and terrifying extension of this is a future conflict that begins or is decisively waged in space. An attack on a country's GPS or early warning satellites would be an act of war with immediate, catastrophic consequences on the ground, crippling civilian infrastructure, financial networks, and military effectiveness. A war in space would not only be a human tragedy, it would likely render entire orbital regions unusable for generations, surrounding our planet with a permanent, impassable shrapnel field that would end the era of space exploration for a century or more, trapping humanity on Earth as a consequence of its own divisions. The antidote to these political and economic dangers is as clear as it is difficult to achieve: sustained international collaboration and a clear, long-term vision that transcends national borders. The International Space Station stands as a shining, albeit fragile, testament to what is possible when nations pool their resources, knowledge, and political capital. It has survived for over 2 decades precisely because it is a joint venture. No single partner can easily cancel it without severe diplomatic repercussions. This model of shared ownership creates stability. A future lunar base or a mission to Mars that is built as an international endeavor, perhaps even with significant commercial partnership, is far more resilient to the whims of a single government. It creates a web of mutual interest that makes it politically costly to withdraw. The journey to the stars is the most expensive and difficult undertaking in human history. It is a burden too heavy for any one nation to bear alone, not just financially but politically. The ultimate message of this 25th danger is that our greatest challenge may not be engineering a faster rocket or a better radiation shield, but rather the ancient, earthly task of learning to cooperate on a global scale. The future in the cosmos depends not only on our technological genius, but on our wisdom to build a foundation of shared purpose and peaceful collaboration here on Earth. After astronauts have endured the immense challenges of interplanetary travel, their arrival at a new world presents a completely different class of danger, one that is grounded in the very soil beneath their boots. This 26th peril forces us to confront the fact that every planetary surface is an alien landscape, shaped by forces we do not fully understand and composed of materials that can be as hostile as they are mysterious. The ground itself becomes an adversary, from the microscopic particles that hang in the thin air to the vast, unseen fractures that snake through the crust below. The first and perhaps most insidious of these threats is the dust, not the benign dust of Earth, but a fiendishly destructive material that behaves in ways that continually defy our expectations. Take the lunar regolith, for example. This isn't soil as we know it. It's a brutal, glass-sharp powder created by billions of years of micrometeoroid impacts pulverizing the Moon's surface without any weather or water to erode it. Each tiny particle is like a miniature shard of jagged glass, and because there's no atmosphere to provide a protective coating, it is electrostatically charged, clinging to everything with a bizarre tenacity. During the Apollo missions, this dust was a relentless nuisance and a genuine hazard. It clogged the intricate seals of sample containers, scratched helmet visors to the point of reducing visibility, and even jammed the joints of the astronaut spacesuits. When tracked back into the lunar module, it filled the air with an acrid, gunpowder-like smell and irritated their eyes and lungs. Now imagine that same dust on a longer-term mission. It would infiltrate every moving part of a habitat, abrade wiring insulation to cause short circuits, and pose a severe, long-term respiratory hazard. Inhaling these microscopic glass shards could lead to a condition similar to silicosis, a debilitating and incurable lung disease, turning a pioneer's new home into a slow-acting poison chamber. Mars presents its own unique version of this dusty danger. The famous Martian red dust is fine as flour and globally pervasive, carried by planet-wide dust storms that can blot out the sun for weeks. While less sharp than lunar regolith due to some wind erosion, its extreme fineness is its own kind of threat. It can seep through the smallest of gaps, contaminating airlocks and living quarters. More alarmingly, Martian soil is now known to be rich in perchlorates, chemicals that are highly toxic to the human thyroid gland. If an astronaut were to inhale dust contaminated with perchlorates, or if it were inadvertently brought inside on a spacesuit and then ingested, it could lead to serious health problems, disrupting metabolism and hormonal function. This means that the simple act of walking on Mars and then returning to a habitat requires decontamination protocols of the highest order, treating the very ground of the planet as a persistent biological hazard. Beyond the dust, the macroscopic terrain itself is a minefield of hidden dangers. The surfaces of the Moon and Mars are ancient, scarred by impacts and volcanic activity, and largely unexplored up close. An astronaut or a rover could be traversing what appears to be a solid plain, only for the ground to collapse into a hidden lava tube or a crevice masked by a thin layer of dust. These natural pitfalls could easily swallow a vehicle or a person, with no possibility of a terrestrial-style rescue. The rock formations are another major concern. On the Moon, the debris fields around craters are littered with sharp, angular basalt rocks, remnants of violent impacts that can shred spacesuit boots or puncture a rover's tire. A simple tear in the sole of a boot might seem minor, but it could compromise the suit's thermal integrity and pressure seal, leading to a life-threatening situation. Every step on an extraterrestrial surface must be taken with extreme caution, as a twisted ankle or a fall onto a jagged rock could mean being stranded miles from the habitat with limited ability for a crewmate to provide assistance in the cumbersome confines of a spacesuit. Adding a profound and unsettling dimension to these surface hazards is the ground's potential to move without warning. We are familiar with earthquakes on Earth, but other worlds have their own versions. The Moon experiences moonquakes, and while some are triggered by tidal forces from Earth, the most powerful are deep tremors that can last for astonishingly long periods, up to 10 minutes or more. Unlike the short, sharp jolts of most terrestrial earthquakes, a major moonquake would be a prolonged, rolling vibration that could seriously destabilize a lunar base's structures, damage sensitive equipment, and trigger landslides on crater walls. Mars, too, has marsquakes as detected by NASA in Sight Lander. While generally less powerful than major earthquakes, they are a stark reminder that the planet is geologically active. The ground shaking on a world where no building codes exist to account for such events could collapse habitats, rupture pressurized domes, and sever power lines, leaving a crew exposed to the planet's unforgiving environment. Finally, there is the danger of the unknown chemical and mineralogical composition of the soil itself. We have broad data from rovers and landers, but we have only sampled a minuscule fraction of these worlds. The soil could contain reactive compounds that, when mixed with the humidity from a habitat's atmosphere or the astronaut's breath, could create corrosive acids that eat away at metal structures and wiring. There might be unexpected catalytic materials that could interfere with life support system chemistry, or bizarre, razor-sharp crystalline structures that form under the unique conditions of low gravity and high radiation. Every scoop of soil collected, every core sample drilled, carries a small risk of uncovering something entirely unanticipated, a substance that could degrade a spacesuit's fabric, a mineral that releases toxic gas when heated, or a biological agent, however unlikely, for which we have no defense. This encapsulates the ultimate challenge of planetary exploration. The courage to step onto a new world is matched only by the humility required to accept that we truly do not know what lies beneath our feet, and that the very ground we seek to conquer might be actively resisting our presence in ways we are only beginning to comprehend. Yet another danger forces us to confront a fundamental paradox of interplanetary travel. The very act of trying to become self-sufficient on a new world could be what ultimately dooms the mission. This 27th peril is the high-stakes gamble of in-situ resource utilization, or ISRU, the ambitious endeavor to live off the land by extracting water, air, and fuel from the alien environments of the Moon or Mars. While it is an absolute necessity for any lasting presence beyond Earth, it is a discipline fraught with unproven technology and the ever-present specter of catastrophic failure in a place where there are no spare part stores and no second chances. The core of the problem is a brutal logistical reality known as the gear ratio. For every kilogram of mass you want to land on the surface of Mars, you need to launch many times that amount from Earth to account for the fuel required for the journey, the landing, and the return trip. This makes the idea of shipping all the water, oxygen, and rocket propellant for a multi-year mission from Earth astronomically expensive and practically impossible. ISRO is the proposed solution, a way to break this tyrannical equation. The vision is elegant. Send a robotic advanced team to extract water from the shadowed craters of the Moon or the subsurface ice of Mars, then use electrolysis to split it into liquid oxygen and hydrogen for breathable air and rocket fuel. A mission like NASA Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, has already proven this is possible in principle, successfully producing oxygen from the carbon dioxide in the Martian atmosphere on a small scale. But scaling this from a coffee maker-sized experiment to an industrial-grade, life-sustaining factory is a leap of terrifying proportions. The dangers inherent in this process are twofold, starting with the immense mechanical and chemical complexity of the equipment itself. An ISRO plant would be a sprawling, industrial facility operating in the most hostile environment imaginable. It would need powerful pumps to move regolith, high-temperature reactors to bake out water ice, intricate filtration systems to purify the resulting resources, and colossal cryogenic freezers to store volatile liquids like liquid oxygen and hydrogen for months or years. Every pump seal, every valve, every electrical connection is a potential single point of failure. Imagine a critical water extraction drill on Mars seizing up because of the abrasive dust we discussed earlier. Or picture a catalyst bed in an oxygen generator becoming poisoned by an unexpected contaminant in the Martian atmosphere, rendering it useless. A failure here isn't just an inconvenience, it is a death sentence. If the crew arrives expecting to find a fully stocked warehouse of supplies and instead finds a silent, broken factory, their mission is over before it even began. They would be stranded with no way to make air to breathe, water to drink, or, most critically, no fuel for their ascent vehicle to leave the planet and begin the journey home. Beyond the risk of outright mechanical failure lies a more subtle and insidious threat: the law of unintended consequences when human industry interacts with an alien environment. We simply do not know the full chemical and mineralogical composition of the lunar or Martian soil. An ISRO process designed to heat the soil to extract water ice might inadvertently also release a trapped volatile gas, something like chlorine or sulfur dioxide, creating a toxic plume that could settle over the landing site and corrode the habitat's exterior or poison the local environment. The act of drilling could destabilize the ground, triggering a collapse into a subsurface cavity or a local moonquake that damages the very base the drill was meant to supply. Furthermore, the waste products of these industrial processes pose their own hazard. What do you do with the tons of processed, potentially chemically reactive regolith left over after you've extracted the water? Piling it up could create unstable slopes that could slide, or dust from the piles could be constantly kicked up by winds or activities, creating a perpetual contamination problem worse than the natural dust alone. We would be acting as planetary engineers with only a fragmentary understanding of the systems we are trying to manipulate, potentially creating a cascade of new problems while trying to solve the old one of survival. This transforms the promise of ISRO from a straightforward engineering challenge into a high-risk, high-reward venture where the crew's survival is directly tied to the flawless performance of the most complex machinery ever deployed on another world. It places an immense burden on the robotic precursors sent ahead of human explorers. They must not only land safely, but also operate autonomously for years, surviving the deep cold of alien nights and the relentless radiation, all while building up the essential stockpiles that will welcome the human crew. A single flaw in that automated chain could turn a future Mars base from a thriving outpost of humanity into a ghost town, a monument to the immense difficulty of truly making a home on a world that was never meant for life. But for all the technical, biological, and psychological dangers we have detailed, none force us to confront the human cost of exploration more directly than the stark, unspoken question of what happens when the ultimate sacrifice is made. This 28th danger is not one of physics or engineering, but of profound ethical and moral weight, the logistical and psychological nightmare of handling a fatality in the utter isolation of deep space. In an environment where every gram of mass and every cubic foot of space is accounted for with mathematical precision, the simple, tragic fact of a human death presents a crisis for which there is no easy protocol, only a series of agonizing choices that would haunt the surviving crew and mission controllers back on Earth. The immediate, brutal question that would arise in the cold silence following a death is what to do with the body itself. The option that seems most respectful on Earth, bringing the fallen explorer home, is fraught with impossible logistical challenges. A preserved human body has significant mass, and on a return journey, every kilogram dedicated to the deceased is a kilogram of food, water, or scientific data that is sacrificed. The power and fuel required to transport the body back to Earth would be immense, effectively burning precious resources to carry out a solemn, yet functionally difficult act of repatriation. Furthermore, the body itself becomes a biological hazard in the enclosed environment of the spacecraft. Without sophisticated refrigeration or preservation equipment, which itself would require more power and space, natural decomposition would begin, creating a serious risk of contamination and disease for the remaining crew. The spacecraft, their only sanctuary, would become, in part, a tomb, a constant and grim reminder of their loss. The alternative is just as unsettling, leaving the body behind. This could mean a burial in the void, releasing the body into the vacuum of space, or interring it on the surface of another world like Mars or the Moon. While this might seem like a poetic final rest among the stars, it raises its own set of profound ethical and even legal questions. Does a nation have the right to claim a celestial body as a permanent cemetery? Would we be contaminating a pristine world with terrestrial biology, undermining the very principles of planetary protection we strive to uphold? And what of the family back on Earth, denied the closure of a gravesite they can ever visit? The decision would be a torturous one, pitting the practical needs of the living against our deepest human instincts for reverence and ritual. There is no precedent for this, no established interplanetary law or universally agreed upon custom to guide such a heartbreaking choice. Beyond the immediate physical dilemma lies the deeper, more corrosive danger, the psychological impact on the surviving crew. Trapped in a small, inescapable metal tube millions of miles from home, they would be forced to continue living and working in the same space where their friend and colleague died. There would be no grief counselors to call, no opportunity for a change of scenery, and no respite from the constant, silent presence of the absent. The crew would have to manage their own shock, grief, and potentially even guilt, all while maintaining the intense focus required to keep the mission and themselves alive. The dynamic of the group would be irrevocably shattered. Could the crew still function as a cohesive, trusting unit? Would the trauma impair their cognitive abilities and decision-making during future emergencies? The stress could fracture the team, leading to conflict, paralyzing depression, or a collective loss of morale that could itself jeopardize the entire mission. This scenario forces our uncomfortable but necessary evolution in our approach to spaceflight. For journeys to Mars and beyond, crews will need to be more than just expert pilots and scientists. They will need to be trained in crisis management and psychological first aid to an extent never before required. Mission protocols will have to include explicit, pre-planned procedures for handling a death, as cold and clinical as that may sound, to prevent the survivors from being paralyzed by the weight of an unthinkable decision in their moment of deepest distress. Ultimately, this danger strips away the last vestiges of romanticism from the endeavor. It confronts us with the raw, unvarnished truth that space exploration is a frontier as deadly as any in human history, and that those who venture into it do so accepting a risk that extends beyond their own lives, casting a long shadow over their crewmates and the very future of the journey itself. As we increasingly equip our spacecraft with thinking machines to manage their immense complexity, we encounter a 29th danger that is as subtle as it is systemic: the creeping peril of over-reliance on artificial intelligence and automation. On the surface, these systems are indispensable. They can process millions of data points per second, manage power flows with superhuman efficiency, and navigate the void with a precision no human hand could ever match. They handle the tedious, constant monitoring that would overwhelm a human crew, freeing them to focus on science and mission objectives. Yet this very dependency creates a technological trap, a situation where the human operators, the intended masters of the mission, can gradually become passengers in their own ship, their critical skills dulled by the comforting, consistent hum of a machine that never seems to sleep or err. The danger isn't that the AI will become malevolent like in science fiction, but that it will fail in a way that is utterly literal, misinterpreting flawed data, encountering an untested scenario, or simply suffering a glitch that a human would instantly recognize as nonsense, but which the machine executes with flawless, catastrophic obedience. This vulnerability was horrifically illustrated by the loss of the Mars Climate Orbiter in 1999. After a flawless 9-month journey to the Red Planet, the spacecraft fired its engine to enter orbit. But instead of settling into its planned path, it dipped too close to the Martian atmosphere and was either torn apart or burned up, vanished forever. The investigation revealed a failure of almost absurd simplicity. One team of engineers had built a crucial piece of navigation software using imperial units, pounds of force, while the spacecraft's own systems expected the data in metric units, newtons. The automation on board and the ground systems checking it did exactly what they were programmed to do. They crunched the numbers with perfect accuracy, but they were crunching the wrong numbers. There was no sanity check, no human intuition to step in and say, "Wait, these trajectory numbers look completely off." The machine faithfully followed its flawed instructions all the way to its own destruction. A stark, multi-million-dollar lesson in how a tiny, human-generated error can be magnified into total mission failure by an automated system that lacks any capacity for context or common sense. The deeper risk lies in what this reliance does to the crew themselves. When systems are highly automated and function perfectly for months on end, a psychological state known as automation complacency sets in. The human brain, always seeking to conserve energy, begins to disengage. Instead of actively monitoring the streams of data, an astronaut might transition into a passive observer, their vigilance dulled by the machine's unwavering reliability. They may start to see what they expect to see on their displays, glossing over a subtle anomaly that a more engaged mind would flag as a warning sign. The real danger emerges when a true emergency finally occurs. It can take precious seconds or even minutes for an astronaut to shift mental gears from that passive monitoring state back into a high-alert, problem-solving mode. In a crisis where every second counts, that cognitive delay can mean the difference between a managed incident and a cascade of failures. Furthermore, if crews rarely practice manual control of their spacecraft, the complex, hands-on skills required to pilot a vehicle, repurpose systems, or perform emergency repairs can atrophy, just like muscle and bone in microgravity. When the screens go dark and the alarms scream, the crew must rely on instinct and training that has been practiced, not just theoretically understood. The challenge, then, is not to discard automation, but to forge a new and more intelligent partnership between human and machine. The goal is to design systems that enhance human judgment rather than replace it. This means creating AI that doesn't just provide answers, but also explains its reasoning and, crucially, expresses its level of confidence. It means building interfaces that clearly highlight anomalies and present information in a way that supports human situational awareness rather than overwhelming it with raw data. Most importantly, it mandates a cultural and training shift where astronauts are continuously tested with realistic, hands-on simulations that force them to take manual control and solve problems without the aid of their digital co-pilot. The balance we must strike is a delicate one. We need the superhuman speed and precision of automation to venture into the cosmos, but we must never let it lull us into forgetting that the final, most important system aboard any spacecraft is the human mind, with its unparalleled capacity for intuition, adaptation, and the kind of creative, out-of-the-box thinking that can never be fully coded into a machine. And so we arrive at the 30th and final danger, a threat that circles back to the very beginning of our journey, but on a scale so vast it forces us to confront our own role in the cosmos. This is not merely a biological or technological peril, but an existential one: the profound and sobering responsibility of interplanetary contamination. After navigating 30 hidden dangers, from the tyranny of rocket fuel to the specter of cosmic radiation, we find that our greatest challenge may not be surviving the universe, but ensuring the universe survives us. This final danger reframes the entire endeavor of space exploration, transforming it from a conquest into a test of our wisdom, our ethics, and our readiness to become stewards of more than just our own world. At its heart, this is a crisis of cosmic etiquette. For centuries, we have viewed new worlds as territories to be claimed and resources to be exploited, projecting our earthly history of colonization onto the stars. But what if we are not the only tenants in this vast universe? The gravest danger of forward contamination, the pollution of a pristine alien environment with our earthly microbes, isn't just the logistical nightmare of false positives in our search for life. It is the philosophical horror of committing an act of unintentional interplanetary genocide. Consider a place like Europa, Jupiter's icy moon. Beneath its frozen crust lies a global ocean warmed by tidal forces, which many scientists believe is one of the most promising places in our solar system to host life. If a future probe, despite our best sterilization efforts, carries a single, resilient extremophile bacterium from Earth into that ocean, the consequences could be catastrophic. That microbe, finding itself in a nutrient-rich environment with no natural predators, could multiply uncontrollably, acting as an invasive species on a planetary scale. It could outcompete and completely extinguish any fragile, nascent Europan life forms that may have been evolving in isolation for billions of years. We would never even know they existed. Our first contact would not be a handshake but an extinction-level event, and we would be the asteroid. This responsibility extends far beyond the ethical. It touches upon one of the most fundamental questions humanity has ever asked: are we alone? By carelessly contaminating other worlds, we risk forever obscuring the answer. We might drill into the Martian permafrost, find a strand of DNA, and celebrate, only to later realize through painstaking analysis that it was a contaminant we brought with us a stowaway from the Kennedy Space Center. The tragedy would be that we destroyed the very evidence we sought, rendering a world scientifically sterile and robbing ourselves of the chance to discover a truly independent genesis of life. The implications are staggering. Finding a second genesis of life, a biology built on a different foundational blueprint than our own DNA-based system, would be the most profound discovery in human history. It would tell us that life is not a fragile, singular accident, but a common, robust force in the universe. Conversely, if we find that life on Mars shares our biochemical roots, it could suggest that life travels between planets, hitching rides on meteorites, and that we are all, in a very real sense, related. But we can only make these universe-altering distinctions if we are certain that what we are looking at is truly alien, and not our own reflection in a dirty mirror. The protocols designed to prevent this, known as planetary protection, are therefore not just bureaucratic hurdles, they are a moral covenant. They are the embodiment of the prime directive from science fiction made real. NASA and other space agencies maintain planetary protection officers whose job is to act as cosmic referees, enforcing rigorous sterilization standards for spacecraft destined for sensitive worlds like Mars or Europa. These spacecraft are assembled in pristine cleanrooms, their components baked in giant ovens, and their every bolt and wire treated with the utmost care to minimize biological burden. This is an acknowledgement that we are not just explorers, we are guests. It is a promise that we will tread lightly, that we will look before we leap, and that we will respect the integrity of other worlds as we would want our own to be respected by any visitors from the stars. Ultimately, this 30th danger brings our journey full circle, connecting the most technical aspects of rocketry and radiation to the most profound questions of our purpose. The 30 hidden dangers of space exploration are not just a list of obstacles to be overcome. They are a mirror held up to humanity, reflecting our ingenuity, our courage, our fragility, and now our maturity. To venture into the cosmos successfully, we must prove that we can manage not only the physics of our spacecraft and the biology of our bodies, but also the ethics of our ambition. The final frontier is not a void to be conquered, but a web of connections to be understood and respected. The greatest test awaiting us among the stars is not whether we can build a faster engine or a stronger shield, but whether we possess the wisdom to explore as guardians, not just conquerors, ensuring that the story of life in the universe continues to be written in countless, diverse chapters, rather than being edited down to a single terrestrial tale. And so, after meticulously navigating a litany of 30 distinct and formidable dangers, we arrive at a sobering realization. The ultimate peril, the one that truly lurks in the deep shadows of the cosmos, may not be on any list at all. This is the unquantifiable danger of the unknown, unknowns, the threats we cannot yet imagine, let alone prepare for, born from the sheer, humbling fact that we are still infants taking our first tentative steps into a universe whose true nature and rules we are only beginning to comprehend. For all our advanced engineering and carefully modeled risks, the history of exploration, both on Earth and in space, teaches us one consistent lesson: the map is never the territory. The most sophisticated simulations and the most exhaustive planning cannot capture the full, chaotic, and often bizarre reality of a new environment. We are venturing into a realm where our fundamental assumptions about physics, biology, and consciousness itself could be challenged in ways we cannot possibly foresee. Consider the very fabric of reality as we understand it. Our spacecraft, our instruments, and our biological models are all built upon the bedrock of classical and quantum physics that we have tested here on Earth. But what if the conditions in the profound emptiness between stars or in the gravitational well of a neutron star reveal subtle new forces or interactions? We already grapple with the mysteries of dark matter and dark energy, which constitute the overwhelming majority of the universe's mass and energy, yet remain completely invisible and unexplained to us. A deep space mission could, in theory, encounter a phenomenon related to these hidden aspects of the cosmos, a region of space with unexpected gravitational lensing, or a strange energy field that interferes with atomic clocks and navigation systems in a way our physics cannot account for. This isn't about encountering alien monsters. It's about the far more disquieting possibility of discovering that some of our most trusted scientific laws have exceptions in the vast, uncharted volumes of the galaxy, leaving our technology suddenly and inexplicably crippled. The biological unknowns are equally profound and deeply personal. We have studied the effects of microgravity and radiation on the human body for decades, but these are largely short-term studies in the relatively protected environment of low Earth orbit. What happens to human physiology after 5, 10, or 20 years in deep space? Could there be a cumulative tipping point effect for radiation damage that we haven't yet observed? One that triggers a sudden, catastrophic systems failure in the body rather than a gradual increase in cancer risk. Or consider our microbiome, the vast ecosystem of bacteria, viruses, and fungi that live in and on us, essential for our digestion, immunity, and even mental health. In the sterile, confined, and high-radiation environment of a long-duration spacecraft, how might this delicate internal jungle evolve? Could we see the emergence of entirely new, opportunistic microbes or a fundamental shift in the gut-brain axis that leads to unforeseen neurological or psychiatric conditions? We are not sending sterile, mechanical astronauts into space. We are sending entire, complex ecosystems, and we have no idea how those ecosystems will transform over a multi-generational journey. This leads to the most profound psychological unknown, the human mind's response to an existence utterly divorced from the planet that shaped it. We have data on 6-month or 1-year missions, but what about a voyage that spans a lifetime or multiple lifetimes aboard a generation ship? The psychological constants we take for granted, the day-night cycle tied to a single sun, the changing seasons, the visual diversity of a natural landscape, the ability to step outside and feel open air would all be gone, replaced by an artificial, monotonous, and deeply unnatural reality. Could this lead to a new form of existential malaise or a species-wide cognitive shift that we cannot predict from our current studies? The very concept of purpose, identity, and culture could warp over generations born and raised in a metal hull. Their only reality, the endless black outside the viewport and the stories of a blue-green world they have never set foot on. The danger isn't just that they might go mad, it's that they might evolve into something else entirely, a new kind of human for whom Earth is a mythological concept, and whose motivations and mental stability become completely unpredictable to their creators. This is why the spirit of exploration must be a careful balance between bold courage and profound humility. To charge forward without a deep respect for the power and mystery of the cosmos is the height of folly. It is the difference between a seasoned sailor who respects the sea and a reckless tourist who underestimates a storm. Our preparation, therefore, cannot stop at building better shields or faster engines. It must involve cultivating a scientific and operational culture that is supremely adaptable, one designed not for the problems we expect, but for the surprises we cannot. This means building spacecraft with open, reconfigurable architectures, not locked proprietary systems. It means training astronauts not just in prescribed procedures, but in the fundamental principles of science and engineering, empowering them to become true pioneers and problem solvers when the instruction manual from Earth no longer applies. It means designing missions with immense margins for error and the flexibility to change course, to observe, and to learn from the unknown rather than blindly charging toward a predetermined goal. The ultimate tool for surviving the unknown unknowns is not a specific piece of technology, but a mindset, a blend of relentless curiosity, intellectual humility, and the resilient creativity to meet the universe on its own terms, ready to be astonished and prepared to be changed by what we find. From the crushing tyranny of the rocket equation to the silent, suffocating vacuum, from the psychological erosion of isolation to the cosmic radiation that rewires the brain itself, our journey through these 30 hidden dangers paints a stark and humbling portrait. We have navigated a gauntlet of perils that target every facet of our existence, shattering our bones, weakening our immune systems, clouding our vision, and challenging our very sanity. We have seen how fire becomes a shape-shifting phantom in microgravity, how a speck of paint transforms into a high-velocity projectile, and how the very ground of another world can be a toxic, treacherous trap. This overwhelming array of threats, from the microscopic to the existential, solidifies one undeniable truth: space is the most comprehensively hostile environment humanity has ever dared to confront. Yet to catalogue these dangers in such stark detail is not an exercise in fear or an argument for retreat. On the contrary, it is the deepest form of respect, a profound homage to the staggering courage of the astronauts who voluntarily face these risks, and to the brilliant, painstaking work of the engineers who dedicate their lives to building walls against the void. Every safety protocol, every redundant system, every hour spent in a simulator practicing for worst-case scenarios is a testament to the human spirit's refusal to be cowed by the universe's indifference. By staring directly into the abyss and understanding its every hidden menace, we are not admitting defeat. We are engaging in the most rigorous preparation possible. We are replacing blind courage with informed resilience. This meticulous process of understanding, acknowledging, and systematically mitigating each one of these 30 hidden dangers is not a barrier to our future among the stars. It is, in fact, the very key that will unlock the solar system. Every problem we solve, every risk we reduce, lays another stone on the pathway to becoming a multi-planetary species. The knowledge gained from protecting astronauts on the space station will build the safer habitats on the Moon. The lessons learned from surviving the journey to Mars will inform the generation ships that may one day sail to the outer planets. Our progress is measured not by the dangers we ignore, but by the ones we have the wisdom to foresee and the ingenuity to overcome. So, as we stand on the precipice of a new era of exploration, let us carry forward not a sense of trepidation, but one of sober determination. The cosmos has issued its challenges, and humanity is rising to meet them, one solved equation, one reinforced hull, one safeguarded life at a time. The journey ahead is long and fraught with hurdles we have yet to even imagine, but the will to explore is woven into our DNA. We venture forth not because it is easy, but because it is a fundamental part of who we are, and because the ultimate reward, a future for humanity among the stars, is worthy of the immense struggle to get there. We would love to hear from you in the comments below which of these 30 hidden dangers surprised or fascinated you the most. And if you enjoyed this deep dive into the final frontier, be sure to subscribe for more journeys.